There are stars in the universe so small, so dim, and so cold that if you were floating right next to one, you might not even realize it was a star at all. These stars don't blaze with the furious heat of the sun. They don't explode in violent supernovas. Instead, they barely glow, clinging to life in the darkness of space. But here's the strangest part. While massive stars live fast and die young, these tiny stars will outlast everything. When the Milky Way has long since faded, when even the black holes have evaporated, these stars will still be burning. They are called ultra-red dwarf stars, and they are the universe's ultimate survivors. Scientists believe they will last for trillions, possibly even quadrillions, of years, far beyond anything we can truly comprehend. That means that, in the grand story of the universe, our sun is nothing more than a brief flash of light, while these tiny, unremarkable stars will still be shining at the very end of time itself. But that's just the beginning of their mystery. Ultra-red dwarfs are a subclass of red dwarf stars, but they push the limits of what we define as a star. They're right on the edge between a true star and something else entirely, something like a failed star, a brown dwarf. They are so small and faint that many of them were completely undetectable until recently. Even though they're all around us, scattered throughout the Milky Way, their faint glow makes them nearly invisible. And that raises an unsettling question. If we've only just begun to detect them, how many more are lurking in the darkness, completely unseen? To understand ultra-red dwarfs, we first need to talk about what makes them unique. These stars are smaller than any other main sequence stars, often just a little bigger than Jupiter. Their temperatures are so low that they barely manage to sustain nuclear fusion, the process that powers the Sun and most other stars. In fact, some of them hover right on the edge of being a brown dwarf, a celestial object that failed to become a star in the first place. But here's where things get even stranger. Because they burn so slowly, they have an estimated lifespan of hundreds of billions, even trillions, of years. That means the universe itself isn't old enough for any ultra-red dwarf to have died of natural causes yet. Think about that. Every single ultra-red dwarf that has ever formed is still burning today. They outlast everything. But what makes these stars truly fascinating isn't just their longevity. It's what they might be hiding. For years, scientists assumed that planets orbiting these tiny stars wouldn't be good candidates for life. Ultra-red dwarfs are small and faint, meaning any planet in their habitable zone would be extremely close to the star. That should make things unstable. Tidal locking, extreme radiation, and constant flares should make life impossible. But new evidence is challenging that idea. Some researchers now believe that planets around ultra-red dwarfs could actually be among the best places to look for alien life. And this is where the mystery deepens. Because ultra-red dwarfs are so faint, their planets don't get much light. This means that any life that exists there would have to adapt to eternal twilight. What would that look like? Could plants survive in such dim conditions? Could animals evolve under skies that never truly brighten? Some theories suggest that life on these planets might be completely unlike anything we've ever imagined, perhaps based on infrared energy instead of visible light. But there's another layer to this mystery. Because these stars are so small, their planets are easier to detect. They create more noticeable dips in brightness when they pass in front of their stars. That means if there's a planet orbiting an ultra-red dwarf, we have a good chance of finding it. And in recent years, astronomers have done exactly that. Some of the most Earth-like exoplanets we've ever discovered orbit these tiny, faint stars. Planets that sit in the habitable zone, where liquid water could exist. Planets that could, in theory, support life. And yet, something strange is happening. Despite their abundance, we aren't finding as many planets as we expected around ultra-red dwarfs. Some scientists think we might be missing them, that our methods for detecting them aren't refined enough yet. But others suggest something far more intriguing. What if these stars are hiding planets in ways we don't understand? What if there's something about these systems that defies our current models of planetary formation? This mystery only deepens when we look at the atmospheres of these planets. Normally, when a planet transits its star, we can analyze the light passing through its atmosphere to determine what it's made of. But ultra-red dwarfs make this incredibly difficult. Their dim light means there's very little for us to analyze. This has left scientists frustrated and excited. Because if we ever do crack the code and find an ultra-red dwarf with an atmosphere rich in oxygen, methane, or other biosignatures, it could be the biggest discovery in human history. But that's not the only thing making these stars mysterious. Ultra-red dwarfs also seem to challenge our understanding of how stars work. For years, we thought that small stars like these wouldn't have much activity. After all, they're dim and burn fuel slowly. But recent observations have flipped that idea on its head. It turns out that ultra-red dwarfs can be some of the most violent stars in the universe. They unleash massive solar flares, far more powerful than anything the sun produces. These flares could sterilize any nearby planets, stripping away atmospheres and making life impossible. But here's the paradox. Despite these violent bursts, their planets still seem to hold onto their atmospheres. How is that possible? Do these planets have some kind of unknown shielding mechanism? Are we missing something fundamental about how these tiny stars interact with their surroundings? And then, there's the question of their numbers. Ultra-red dwarfs are thought to be among the most common stars in the universe. Some estimates suggest that for every large star like our Sun, there are dozens, if not hundreds, of ultra-red dwarfs. That means our entire galaxy could be filled with them. But if that's the case, why aren't we detecting more of them? Are they simply too faint, or is there something about their nature that makes them even harder to find than we thought? Some scientists believe that ultra-red dwarfs could hold the key to solving some of the biggest questions in astronomy. Because they live so long, they could provide insight into the early days of the universe. Some of these stars could be nearly as old as the Milky Way itself, meaning they might contain clues about how the first stars formed, how galaxies evolved, and even how the first planets came into existence. And here's where things get truly mind-bending. Because ultra-red dwarfs burn so slowly, they will be the last stars shining in the universe. Long after the sun has burned out, long after even the brightest supergiants have gone dark, these tiny, dim stars will still be burning. They will outlive everything. And that raises a strange possibility. What if the final civilizations in the universe are born on planets orbiting ultra-red dwarfs? When everything else has gone dark, these tiny, faint stars might be the last beacons of light, keeping the cosmos from falling into total darkness. So the real question is, what are we missing? What secrets are these ancient, undying stars keeping from us? Are they hiding Earth-like worlds just out of sight? Are they home to alien life that thrives in conditions we never thought possible? Or do they hold clues about the fate of the universe itself? One thing is certain, ultra-red dwarfs are everywhere, and yet we barely understand them. But as telescopes get better, as our methods improve, we might finally start to uncover their secrets. And when we do, we might just find something that changes everything we thought we knew about the universe. The idea that ultra-red dwarfs could be the last shining stars in the universe is more than just speculation, it's an inevitable reality. Stars like our Sun have relatively short lifespans, burning through their fuel in about 10 billion years before swelling into red giants and collapsing into white dwarfs. Massive stars live even shorter lives, burning out in just a few million years. But ultra-red dwarfs? They are different. Their incredibly slow fusion process means they can last for hundreds of billions of years, potentially even trillions. That's longer than the universe has existed so far. To put that into perspective, our universe is about 13.8 billion years old. That means every ultra-red dwarf star that has ever formed is still shining today. Not a single one has burned out yet. And since they form constantly, the number of these stars in the cosmos is only increasing. This means that long after the last sun-like star fades away, long after every galaxy has drifted apart, and even after the last black hole evaporates, these tiny, faint stars will still be burning in the darkness. This realization raises a fascinating question. Could the final civilizations in the universe be built around ultra-red dwarf stars? Imagine a future where every other source of energy has disappeared, and only these small, dim stars remain. Would the last intelligent beings in existence find refuge on planets orbiting these dying embers? Would they build their final cities under skies of perpetual twilight, drawing power from the faint heat of the last stars? It's a haunting thought, one that stretches beyond human history and into the distant future of the cosmos itself. But before we get too far ahead of ourselves, let's go back to the present. Right now, ultra-red dwarfs are not just mysterious. They're actively rewriting what we thought we knew about star formation, planetary science, and even the search for extraterrestrial life. These tiny stars challenge our understanding in so many ways. One of the biggest surprises is just how active they can be. For years, astronomers assumed that smaller stars would be relatively calm. After all, they burn through their fuel so slowly that they should have low levels of magnetic activity. But when scientists finally started observing ultra-red dwarfs up close, they found something shocking. Many of these stars produce solar flares that are far more powerful than anything the sun has ever unleashed. In some cases, these flares are so strong that they can double, or even triple the brightness of the star in just a few minutes. This presents a paradox. On one hand, ultra-red dwarfs are often considered the best candidates for hosting habitable planets because they are so long-lived. But on the other hand, their violent flares could make life nearly impossible. A single flare from an ultra-red dwarf can release deadly radiation, stripping away atmospheres and bombarding planets with high-energy particles. If Earth were orbiting a star like this, our atmosphere might have been eroded away billions of years ago, leaving the planet a barren wasteland. Yet, despite this, some planets around these stars still seem to have atmospheres. That's where the real mystery begins. Scientists are now trying to figure out how these planets are holding on to their air, despite being blasted by radiation on a regular basis. Some theories suggest that thick atmospheres or strong magnetic fields could help protect them. Others believe that life, if it exists, might have adapted in ways we can't even imagine, possibly surviving underground or beneath thick layers of ice. And then there's the question of water. On Earth, life thrives wherever there's liquid water. But what about planets orbiting ultra-red dwarfs? Because these stars are so dim, their habitable zones, the regions where temperatures allow for liquid water, are extremely close to the star. This means that any planet in the habitable zone is likely tidally locked, with one side always facing the star and the other side trapped in eternal darkness. At first glance, this seems like a death sentence for habitability. The day side would be scorching hot, while the night side would be frozen solid. But new models suggest that some of these planets could have just the right atmospheric conditions to circulate heat between the two sides. If that's the case, the region between light and dark, the so-called terminator zone, could be a stable, temperate place where life might flourish. But the biggest question of all is, have we already found an ultra-red dwarf with an Earth-like planet? The answer is, maybe. One of the most exciting discoveries in recent years was the TRAPPIST-1 system, which consists of a tiny, ultra-cool red dwarf star surrounded by 7 Earth-sized planets. 3 of these planets are in the habitable zone, meaning they could, in theory, have liquid water on their surfaces. But here's where it gets even more interesting. Unlike most stars, TRAPPIST-1 is so dim that it barely emits visible light. If you were standing on one of its planets, the sky would be a deep, eerie red. The sun would appear much larger in the sky, but it wouldn't be bright. It would be more like a massive, glowing ember hanging in the darkness. This raises an entirely new question. If life exists on planets around ultra-red dwarfs, how would it adapt to such an environment? Would plants evolve to absorb infrared light instead of the visible light we're used to? Would eyes develop differently to see in lower light conditions? Would life forms be nocturnal by default, simply because their world never experiences true daylight? The possibilities are endless. And what if life on these planets has already evolved beyond simple organisms? Could we be overlooking civilizations that thrive under the dim glow of these tiny stars, simply because we've been searching for Earth-like conditions instead of recognizing alien possibilities? Some scientists believe that the search for life needs to focus more on ultra-red dwarfs, simply because they are the most common type of star in the universe. If life can exist around these stars, it could mean that the universe is far more populated than we ever imagined. But there's still so much we don't know. Why are some ultra-red dwarfs more active than others? Why do some of their planets retain atmospheres despite intense radiation? And why do we keep finding planets in places where we thought they shouldn't exist? One thing is certain: the more we study ultra-red dwarfs, the more questions we uncover. These tiny stars may not seem like much at first glance, but they could hold the answers to some of the biggest mysteries in the universe. Are they home to alien life? Are they the last stars that will ever shine? And could they be the key to understanding the fate of the cosmos itself? We may not have all the answers yet, but one thing is clear: ultra-red dwarfs are not just ordinary stars. They are cosmic enigmas, burning quietly in the darkness, waiting for us to uncover their secrets. Ultra-red dwarfs remain some of the most mysterious objects in the universe, not only because of their sheer numbers but because they defy our expectations of what a star should be. Unlike the massive, blazing stars that dominate the night sky, these tiny, barely glowing celestial bodies are often invisible to the naked eye, hiding in the darkness like cosmic ghosts. And yet, despite their faintness, they could hold the key to some of the most profound questions in astronomy, from the nature of habitability to the ultimate fate of the universe itself. One of the strangest aspects of ultra-red dwarfs is how they challenge our understanding of stellar evolution. For most stars, their life cycle follows a predictable path, forming from vast clouds of gas, shining brightly for millions or billions of years, and then eventually dying in a dramatic event like a supernova or a slow fade into a white dwarf. But ultra-red dwarfs don't follow this pattern. Instead, they burn their fuel so slowly that they could outlive every other type of star. This means that in the distant future, long after our sun has expanded into a red giant and collapsed into a white dwarf, ultra-red dwarfs will still be burning. In fact, not a single one has had time to die yet, simply because they last so long. This makes them unique among stars. We are living in an era where every ultra-red dwarf that has ever formed is still shining. This also means that the first ultra-red dwarf to ever die might not do so for hundreds of billions, or even trillions, of years. To put this into perspective, consider the estimated lifespan of a typical ultra-red dwarf. A star like TRAPPIST-1, one of the most famous ultra-red dwarfs in our galaxy, has an expected lifetime of at least 10 trillion years. That's more than 700 times the current age of the universe. In other words, these stars are effectively immortal on cosmic timescales. But why do they last so long? The secret lies in their structure and how they generate energy. Unlike larger stars, which burn through their hydrogen fuel quickly and develop layers of different elements, ultra-red dwarfs are fully convective. This means that their fuel is constantly being mixed throughout the star, preventing it from forming a helium core and extending its lifespan dramatically. While massive stars go through their fuel in just a few million years, ultra-red dwarfs sip their hydrogen supply at an incredibly slow rate, ensuring that they can keep burning for trillions of years. This unique property also means that these stars will never experience the same kind of violent deaths as more massive stars. While a star like our Sun will eventually shed its outer layers and collapse into a white dwarf, an ultra-red dwarf will instead simply fade away over trillions of years, gradually cooling down until it becomes a black dwarf, a theoretical object that doesn't yet exist because the universe isn't old enough for one to have formed. But what happens to the planets that orbit ultra-red dwarfs as they evolve? Could life persist around these stars for trillions of years, long after the rest of the universe has gone dark? This question has intrigued scientists for years, especially because ultra-red dwarfs are known to host a surprising number of exoplanets. Recent studies suggest that ultra-red dwarfs are among the most prolific planet-forming stars in the galaxy. In fact, some astronomers believe that the majority of rocky planets in the universe may orbit stars like these. If that's true, then it means that the most common type of habitable world might not be one that orbits a sun-like star, but instead one that orbits a small, dim, ultra-cool red dwarf. This possibility has huge implications for the search for extraterrestrial life. Traditionally, scientists have focused on searching for Earth-like planets orbiting sun-like stars, assuming that conditions similar to our own would be the most likely places for life to emerge. But if ultra-red dwarfs are the most common type of star, and they are capable of hosting habitable planets, then we may have been looking in the wrong places all along. One of the most famous examples of an ultra-red dwarf with potentially habitable planets is TRAPPIST-1. This tiny, dim star, located just 40 light-years away from Earth, has 7 rocky planets orbiting it, 3 of which are in the star's habitable zone. This means that these planets could, in theory, have liquid water on their surfaces. But the reality is far more complicated. Because ultra-red dwarfs are so small and dim, their habitable zones are extremely close to the star. This creates a number of challenges for habitability. First, any planet in this region is likely tidally locked, meaning that one side always faces the star while the other side is trapped in permanent darkness. This could lead to extreme temperature differences, with one side scorching hot and the other side frozen solid. However, some models suggest that a thick enough atmosphere or ocean currents could help distribute heat more evenly, creating a habitable, twilight zone between the two extremes. Another major challenge is radiation. Despite their small size, ultra-red dwarfs can produce powerful stellar flares that blast their planets with high-energy radiation. These flares could strip away atmospheres, destroy organic molecules, and make it difficult for life to survive on the surface. However, some planets may have strong magnetic fields that protect them, or life may exist underground, shielded from the radiation. In fact, some researchers believe that if life exists on planets orbiting ultra-red dwarfs, it might look very different from anything we know. Instead of plants that rely on visible light for photosynthesis, organisms on these planets might have evolved to use infrared light instead. Some have even speculated that alien plants on these worlds could be black instead of green, absorbing as much of the dim light as possible to maximize energy production. But could intelligent life develop under these conditions? This is one of the biggest unanswered questions in astrobiology. On Earth, complex life took billions of years to evolve, and some scientists wonder if the same timescales would apply to planets around ultra-red dwarfs. Given that these stars last for trillions of years, could it be possible that some civilizations have had lifespans far longer than anything we could imagine? If so, these civilizations would have had the opportunity to develop technology and knowledge that is beyond anything we could comprehend. Some theorists even speculate that if there are advanced extraterrestrial civilizations, they may have chosen to settle around ultra-red dwarfs because of their longevity. If a species wanted to build an empire that lasted for trillions of years, what better place to do it than around a star that will outlive the universe itself? This brings us to one of the strangest and most unsettling possibilities. What if the first intelligent life in the universe has yet to evolve? If ultra-red dwarfs last for trillions of years, and their planets have stable conditions for life, then it's possible that the peak of intelligent life in the universe might not happen for billions or even trillions of years from now. In other words, we may be among the very first intelligent beings to emerge in the cosmos, with the majority of civilizations still waiting to be born in the distant future. This idea, known as the delayed intelligence hypothesis, suggests that the most advanced civilizations might exist long after our own has disappeared. If that's the case, then the search for extraterrestrial life might not just be about finding aliens today. It might be about understanding the conditions that will allow life to flourish in the distant future. Ultra-red dwarfs may hold the answers to some of the biggest mysteries of the universe, from the origins of life to the fate of the cosmos itself. They may be the last beacons of light in a dying universe, the final refuges of intelligent life long after the last sun-like star has burned out. And if that's true, then the real question isn't whether we are alone in the universe. It's whether we are simply too early to witness the peak of cosmic civilization. If ultra-red dwarfs are the final refuges of life in the universe, then the implications are staggering. It means that while our own civilization is racing against the clock, facing threats from everything from asteroid impacts to self-inflicted disasters, there could be other civilizations, ones that will emerge long after we are gone, that will exist in a far more stable and predictable universe. Instead of living on borrowed time like we are, they may have trillions of years to evolve, expand, and explore without the fear of their star dying. This idea completely reshapes our understanding of where and when intelligent life might emerge. For decades, the search for extraterrestrial intelligence, SETI, has focused on sun-like stars, assuming that civilizations would arise in environments similar to our own. But if ultra-red dwarfs are the most common stars, and if they offer stable conditions for life for incomprehensibly long periods, then we may need to rethink everything. It might not be the case that we're simply unlucky in not detecting alien signals. It might be that intelligent life simply hasn't had enough time to become widespread yet. In this scenario, we would be the precursors, the early ones, the species that appeared before the true cosmic golden age of intelligence. And that raises another fascinating question. If we are among the first intelligent species, do we have a responsibility to preserve knowledge for those who come after us? If civilizations that arise around ultra-red dwarfs won't appear for billions or trillions of years, could we leave behind some form of information, a cosmic message in a bottle, that tells them about us? Could we build monuments that would survive for eons? Or even leave a permanent record in the fabric of space-time itself? Some scientists have proposed that we could encode messages into the structure of long-lived materials, like diamond or artificial structures built in deep space. Others have suggested that we could send information using neutrinos or gravitational waves, forms of communication that might survive far longer than radio signals. And then there's an even more radical idea. What if we could encode information directly into the fundamental particles of the universe itself, ensuring that our knowledge outlives even the longest-lived stars? But perhaps the most unsettling possibility is this. If ultra-red dwarfs are the eventual homes of future civilizations, is it possible that some ancient species has already done the same for us? Could there be hidden messages, waiting to be discovered, left behind by a civilization that existed before our own? If intelligent life is rare but long-lived, then perhaps the best place to search for evidence of extraterrestrials isn't in the chaotic and short-lived environment of sun-like stars, but around the stable and ancient ultra-red dwarfs, where knowledge could be preserved for trillions of years. This brings us to an even deeper mystery. What if these tiny, dim stars are more than just the last survivors of the universe? What if they are the ultimate witnesses to cosmic history? Consider this. Ultra-red dwarfs will live through every future stage of cosmic evolution, outlasting galaxies, black holes, and even the expansion of the universe itself. As the cosmos grows darker, as other stars fade into nothingness, ultra-red dwarfs will still be there, burning slowly, defying the inevitable decay of everything else. This makes them more than just stars. They are cosmic time capsules, relics of a universe that once burned bright but will one day fade into cold emptiness. If there is any chance of life surviving until the very end, it will be around these stars. And if civilizations can find a way to adapt to the dim, infrared glow of these long-lived suns, then they might outlive even the concept of time itself. But what happens when even ultra-red dwarfs reach the end of their lifespans? What will the universe look like when the last of these ancient stars finally fades away? The answer takes us to the end of time itself. The death of an ultra-red dwarf is not an explosive event. There will be no dramatic supernova, no burst of radiation to mark its passing. Instead, it will simply cool, dimming over trillions of years until it no longer emits any light at all. It will become a black dwarf, a theoretical object that does not yet exist, because the universe isn't old enough for any star to have cooled that much. Black dwarfs are the final fate of stars like ultra-red dwarfs. They are essentially frozen remnants of what was once a star, no longer emitting heat or light, just drifting through the void as the last echoes of a universe that once blazed with energy. In the far future, as the universe continues to expand, black dwarfs will be the only objects left, silent, lifeless, and cold. But even here, at the very end, there may be a strange kind of activity. Some theories suggest that, over an unfathomably long timescale, even black dwarfs could decay, their atoms breaking apart due to quantum effects. If this is true, then the final moment of the universe could be the slow disintegration of these last remaining objects, as the last bits of matter dissolve into nothingness. And yet there is still one final possibility, one last mystery. If civilizations do arise around ultra-red dwarfs, and if they are capable of manipulating the fundamental laws of physics, then could they find a way to escape this fate? Could they engineer a way to survive beyond even the last black dwarf? Some theorists have speculated that advanced civilizations could manipulate the fabric of space-time itself, escaping into parallel universes or even creating new universes where life could continue. If that's the case, then ultra-red dwarfs may not just be the last homes of life in this universe. They could be the launch pads for life to move beyond it entirely. Ultra-red dwarfs are far more than just small, dim stars. They are the quiet survivors of the cosmos, the last sources of warmth in a dying universe, and possibly the ultimate cradles of life. Their long lifespans mean that they will bear witness to the entire history of existence, from the first galaxies to the last fading remnants of a darkened cosmos. And if intelligent life does arise around these stars, then those beings will experience a universe far different from our own, one where time moves at an entirely different pace, where the stars barely change, and where their civilizations might last longer than we can even comprehend. For now, we can only speculate about what the distant future holds. But one thing is certain: as the universe grows older and colder, ultra-red dwarfs will remain, burning faintly in the cosmic darkness, waiting for the civilizations of the future to find them. And perhaps, one day they will. Ultra-red dwarfs stand as the last bastions of energy in a universe that is slowly running out of it. When we think about the ultimate fate of the cosmos, we often picture a vast, empty void, cold, lifeless, and silent. But for trillions upon trillions of years, ultra-red dwarfs will still be burning, still providing light and heat, still defying the inevitable. If life continues to exist anywhere in the universe far into the future, it will almost certainly be around these stars. And that raises an even deeper question: what would life in such an environment look like? Our own planet orbits a star that is relatively young and energetic, producing a broad spectrum of light, including the visible light that most life forms on Earth depend on. But ultra-red dwarfs emit almost exclusively in the infrared range. This means that if evolution were to take place on a planet orbiting one of these stars, the very nature of life itself would be different. Eyes, at least as we know them, might not even exist. Instead of seeing in the visible spectrum, creatures on such a planet would likely have evolved infrared vision, allowing them to detect heat rather than color. Plants, instead of being green, would likely be black, absorbing as much of the faint infrared light as possible to maximize photosynthesis. But the real challenge for life on an ultra-red dwarf planet wouldn't just be the different type of light, it would be the long, drawn-out cycles of time. Because these stars burn their fuel so slowly, the planets orbiting them would be subject to conditions that remain stable for billions, even trillions, of years. This means that evolution wouldn't happen at the same frantic pace as it has on Earth, where rapid changes in climate and environment have driven adaptation. Instead, life might take a much longer time to develop. In fact, if intelligent life does arise around an ultra-red dwarf, it may experience time in a way that is fundamentally different from how we do. Imagine a civilization that evolves on a planet orbiting an ultra-red dwarf, a world where the conditions have remained the same for longer than the entire history of our solar system. To such a species, the concept of change might be completely alien. While human civilizations rise and fall in mere thousands of years, a civilization around an ultra-red dwarf might last for millions, even billions, without any major disruptions. Their science, their entire way of thinking might be built around the idea that the universe is stable and unchanging, because, from their perspective, it is. But there's an even more fascinating possibility. If intelligent life around ultra-red dwarfs develops at a much slower pace than it does around sun-like stars, then we might be among the earliest civilizations in the universe. This could explain why we haven't yet detected any signs of intelligent extraterrestrial life, because, simply put, it hasn't had enough time to emerge. The vast majority of habitable planets may still be waiting for life to develop, and it might not be for trillions of years before the universe is truly filled with civilizations. This has profound implications for the search for extraterrestrial intelligence. If we're looking in the wrong place, if intelligent life is more likely to exist around ultra-red dwarfs than around sun-like stars, then we might be missing our best chance at finding it. Most SETI efforts focus on looking for radio signals from planets orbiting stars like our Sun, under the assumption that other civilizations would be similar to ours. But if the real action is happening around ultra-red dwarfs, then we may need to rethink our approach entirely. Even more intriguingly, if ultra-red dwarfs are the long-term homes of life, then it's possible that civilizations that do arise there will be fundamentally different from us in ways we can't even imagine. Our species is shaped by urgency. Our sun has a limited lifespan, our planet's climate is unstable, and our survival depends on adapting quickly. But a species that evolves around an ultra-red dwarf may have no concept of urgency at all. They may develop technology at an incredibly slow pace, refining their knowledge over millions of years rather than thousands. Their civilizations may not experience war, collapse, or rapid transformation, because they have no need to. This raises an almost unsettling thought. What if there are already ancient civilizations around ultra-red dwarfs that have been watching the universe unfold for billions of years? To them, we might seem like a species that appeared and disappeared in the blink of an eye, a brief flash of activity before fading into cosmic silence. If they exist, they may have witnessed the birth and death of entire galaxies while remaining unchanged themselves. But even ultra-red dwarfs, despite their immense lifespans, will eventually reach their end. The universe, as it continues to expand, will become colder and darker. Matter itself may one day break down, and even the last ultra-red dwarfs will cool into black dwarfs, radiating away their final heat until nothing remains. This is the true endgame of the cosmos, a universe where even the longest-lived stars have faded into darkness, where no new energy is being produced, and where all that remains is the slow, inevitable drift into oblivion. Yet, even in this ultimate darkness, the question remains, could something survive? Could a sufficiently advanced civilization find a way to outlast even the death of the last stars? Some theories suggest that it might be possible for life to persist in ways we can barely comprehend. If a species were to develop the ability to manipulate space-time itself, they might create artificial energy sources, harvesting the quantum fluctuations of empty space. Others have suggested that civilizations could transfer their consciousness into forms that no longer require physical energy, existing as patterns of information in the fabric of the universe itself. And then there is the most audacious idea of all, that a civilization could escape the dying universe entirely. If higher dimensions exist, if wormholes are real, or if there are ways to generate new universes, then the last survivors of the cosmos may not fade into nothingness. Instead, they may find a way to begin again, creating a new reality where life can flourish once more. Ultra-red dwarfs may be small, but they hold within them the greatest mysteries of existence. They challenge everything we think we know about the universe, about time, about life, and about the ultimate fate of everything. They remind us that the cosmos is far stranger, and far more complex, than we could ever imagine. And perhaps, as we continue to explore the vastness of space, we will one day find answers to the questions they raise. But until then, they remain as they always have, burning quietly, waiting, as the rest of the universe rushes toward its inevitable fate. Ultra-red dwarfs stand as cosmic sentinels, outlasting not just their larger stellar counterparts, but potentially even the very fabric of the universe as we understand it. They challenge us to rethink our assumptions about what it means for a star to be alive, what it means for a planet to be habitable, and even what it means for a civilization to endure. While we are accustomed to the idea that stars are bright, short-lived beacons of nuclear fusion, ultra-red dwarfs defy that narrative by burning so slowly that they may outlive everything else in existence. But to fully appreciate their significance, we must go deeper. We must examine their internal structures, the physics that allows them to be so efficient, and the unique conditions they create in their planetary systems. The reason these stars can persist for so long is due to a fundamental difference in how they operate compared to Sun-like stars. Larger stars, including our Sun, undergo fusion primarily in their cores, where immense pressure and heat allow hydrogen to be converted into helium. However, because the energy generated in the core has to travel outward through various layers before being radiated into space, much of the hydrogen in a Sun-like star never gets used. Ultra-red dwarfs, on the other hand, are fully convective. This means that their interiors are constantly being stirred, with hot plasma from the core rising to the surface and cooler plasma sinking downward. This process allows them to use their fuel far more efficiently, ensuring that nearly all of their hydrogen eventually undergoes fusion. As a result, they burn at a much slower rate, making them the most fuel-efficient stars in the universe. While a star like the Sun may last for about 10 billion years, an ultra-red dwarf can persist for hundreds of trillions of years, stretching across time spans so vast that they make the entire history of our universe so far look like a fleeting moment. This raises an even more intriguing possibility. If ultra-red dwarfs are still in their infancy now, then the universe is not yet old enough to have seen the full impact of what these stars can do. In other words, we are living in an era where ultra-red dwarfs have barely begun to reveal their potential. The true cosmic drama surrounding these stars may not play out for another trillion years. That is a staggering realization because it suggests that the universe is still in its early days, still in the process of setting the stage for what might be its longest and most important act. But what about the planets that orbit these stars? While much of the discussion about habitable worlds has centered around sun-like stars, ultra-red dwarfs have recently emerged as some of the most promising candidates for hosting life. The reason for this lies in the nature of their habitable zones, the regions around a star where temperatures are just right for liquid water to exist. Because ultra-red dwarfs are so small and dim, their habitable zones are much closer to the star than the one we have in our solar system. A planet orbiting an ultra-red dwarf in the habitable zone would likely have an orbit measured in days or weeks rather than years. However, this proximity to the star introduces a unique challenge: tidal locking. When a planet orbits very close to its star, gravitational forces can cause one side to always face the star while the other remains in perpetual darkness. This is similar to how the moon always shows the same face to Earth. A tidally locked planet around an ultra-red dwarf would have one hemisphere bathed in eternal daylight and the other shrouded in endless night. This may seem like a recipe for extreme conditions, with one side boiling hot and the other freezing cold, but simulations suggest that a thick enough atmosphere could distribute heat efficiently, allowing for a stable climate along the planet's terminator, the twilight zone where day meets night. If life exists on such a planet, it might be concentrated in this narrow band of eternal dusk. Imagine a world where the sun never moves in the sky, where one side of the horizon glows with the constant, deep red light of an ultra-red dwarf, while the other fades into the darkness of space. The ecosystems on such a planet would likely be vastly different from anything on Earth. Plants might evolve to absorb infrared light, looking nothing like the green vegetation we are familiar with. Instead, they could appear dark or even black to maximize their ability to capture energy from their dim star. And if intelligent life developed in such an environment, how would it perceive time? Would a civilization on a tidally locked world develop a concept of day and night? Or would they experience time as something more abstract? Would they think of the universe as static and unchanging, or would they recognize the slow, inexorable movements of celestial bodies over long timescales? Another challenge for life on planets around ultra-red dwarfs is the intense stellar activity these stars exhibit in their early years. While ultra-red dwarfs are long-lived, they tend to be highly active in their youth, producing powerful solar flares and bursts of radiation that could strip away atmospheres or sterilize planetary surfaces. This presents a paradox. The very stars that might be the best long-term homes for life are also some of the most dangerous in their infancy. If a planet can hold onto its atmosphere long enough for the star to settle into a quieter phase, then it might become one of the most stable environments in the universe. But many planets may not be so lucky. Yet, despite these challenges, ultra-red dwarfs remain some of the best places to search for extraterrestrial life. The reason is simple. They are the most common type of star in the universe. While massive stars like blue giants and supergiants dominate the night sky with their brilliance, they are incredibly rare. Ultra-red dwarfs, on the other hand, make up the vast majority of stars in the Milky Way. If life can exist around these stars, then the sheer numbers suggest that habitable worlds might be far more common than we ever imagined. This has major implications for the future of humanity. If we ever expand beyond Earth and establish colonies in space, ultra-red dwarfs may be our ultimate destination. Their incredible longevity means that planets orbiting them could remain habitable long after the sun has burned out. If our species, or our descendants, survive long enough, we may one day migrate to the worlds of ultra-red dwarfs, seeking refuge in their slow-burning warmth as the rest of the cosmos grows cold. But there is an even more mind-bending possibility to consider. If ultra-red dwarfs are the best long-term hosts for life, then perhaps the first truly interstellar civilizations will arise not from planets like Earth, but from planets orbiting these stars. If so, they may already be out there, watching the universe unfold across vast eons, their civilizations developing at a pace incomprehensible to us. To them, we might appear as little more than a brief anomaly, a species that appeared and vanished in the blink of an eye. And if such civilizations exist, what would they think of us? Would they see us as primitive beings struggling to understand the vastness of the cosmos? Would they view us with curiosity, with indifference, or with something else entirely? The mystery of ultra-red dwarfs is more than just a question of astrophysics. It is a question of time itself. These stars are the keepers of the distant future, the last great sources of light in a universe that is destined to grow darker. They remind us that the cosmos is not just a place of rapid, explosive events, but also a place where time stretches across scales so vast that even our own history feels insignificant. And perhaps, as we continue to explore and learn, we will one day find ourselves in the company of those who have been watching for far longer than we can imagine. Ultra-red dwarfs challenge our understanding of time on a cosmic scale. To grasp their significance, we must step back and consider the fate of the universe itself. The stars we are familiar with, like the sun, burn brightly but briefly, consuming their fuel in a few billion years before collapsing into white dwarfs or exploding as supernovae. But ultra-red dwarfs operate on a completely different timescale. They burn so slowly and efficiently that they may outlive every other type of star in existence. In fact, some of the youngest ultra-red dwarfs we observe today will still be burning trillions of years from now, long after the last supernova has faded, after the last galaxies have begun to drift apart, after the cosmic background radiation itself has cooled to near absolute zero. These stars will be the final beacons of warmth in an otherwise dying universe, their faint glow persisting in the cold void while all else succumbs to entropy. But what does this mean for the potential civilizations that might exist around them? If life can take root around ultra-red dwarfs, then such life could have an incomprehensibly long time span to evolve and develop. Imagine a species that is not bound by the fleeting lifetimes of sun-like stars but instead has hundreds of trillions of years to advance. What would their concept of progress look like? What would their understanding of the universe be? Would such civilizations even recognize time as we do? Our own sense of history is shaped by a world where change is rapid. Civilizations rise and fall within mere thousands of years. But on a planet orbiting an ultra-red dwarf, where nothing changes for millions or even billions of years, a species might develop an entirely different perspective. Progress might be measured not in decades or centuries but in epochs. Perhaps their technological advancements are imperceptibly slow by our standards, unfolding over spans of time that would seem stagnant to us but feel natural to them. This raises another question. If intelligent life emerges around ultra-red dwarfs, would we even be able to recognize it? We often think of alien civilizations in human terms, technological, structured, building things we can understand. But what if a civilization that evolved around an ultra-red dwarf operates on timeframes so slow that their actions seem like geological processes to us? What if, instead of building cities and spacecraft, their form of progress is something beyond our comprehension, something that takes millions of years to even manifest? And what if such civilizations have already existed for billions of years, hidden from our detection simply because their way of existing is so vastly different from our own? If they perceive time differently, their communication, travel, and even their very concept of existence might be so unrecognizable that we wouldn't even know they were there. Ultra-red dwarfs force us to confront the idea that the universe is far bigger and far more complex than we assume. They force us to acknowledge that intelligence, if it arises in other places, may not conform to anything we would recognize. We might be looking for fast, dynamic, recognizable signs of life, radio signals, spacecraft, artificial megastructures, while missing the possibility that life around ultra-red dwarfs exists in a way that doesn't fit our understanding at all. But beyond these speculative ideas, ultra-red dwarfs also present a more practical mystery. How many of them actually host planets that could support life? Because these stars are so small and dim, finding planets in their habitable zones is challenging. Unlike the dramatic transits of larger planets passing in front of bright stars, the subtle dips in brightness caused by Earth-sized planets around ultra-red dwarfs are harder to detect. But in recent years, discoveries like the TRAPPIST-1 system have shown that ultra-red dwarfs are not only capable of hosting planets, but may do so frequently. TRAPPIST-1 is a small, ultra-cool red dwarf star located about 40 light-years away, and it has an extraordinary planetary system. It hosts at least 7 Earth-sized planets, 3 of which are in the habitable zone. This discovery was groundbreaking because it provided the first real evidence that planets around ultra-red dwarfs could be abundant, and that some of them could potentially harbor liquid water. However, despite the excitement, these planets also present challenges. Because they orbit so close to their star, they are exposed to extreme stellar flares in their early years. Some scientists worry that such flares might strip away atmospheres, making these planets barren and uninhabitable. Others argue that if a planet has a strong magnetic field or a thick enough atmosphere, it could withstand the flares and remain habitable. The key question is, how many ultra-red dwarf planets have managed to retain their atmospheres over time? If the answer is, most of them, then the number of potentially habitable planets in the universe could be far greater than we ever imagined. If the answer is, almost none, then the search for extraterrestrial life becomes more complicated. Yet, even if conditions for life are harsh, that doesn't mean life cannot exist. Life on Earth has shown an incredible ability to adapt to extreme environments. Deep in the ocean, where sunlight never reaches, life thrives near hydrothermal vents. In the coldest, driest deserts, microscopic organisms survive. Even in radioactive wastelands, bacteria have found ways to endure. If life can exist in these conditions, then perhaps it can also exist on planets orbiting ultra-red dwarfs, provided the right chemical building blocks are present. And if we do find life on one of these distant worlds, it will fundamentally change our understanding of our place in the universe. It would mean that life is not a rare accident, confined to the fragile conditions of Earth, but something that can emerge in environments completely unlike our own. It would mean that even in the most dimly lit corners of the cosmos, life finds a way. But there is an even bigger question. If life is common around ultra-red dwarfs, what happens when their stars eventually die? Because these stars burn for so long, their deaths are not something we will witness anytime soon. But in the far, far future, hundreds of trillions of years from now, even ultra-red dwarfs will run out of fuel. Unlike massive stars that explode in dramatic supernovae, ultra-red dwarfs will simply fade away, their fusions slowing to a crawl until they become cold, dark remnants of what they once were. This means that any life that depends on them will eventually have to face the reality of a dying star. If intelligent civilizations develop around these stars, would they find a way to survive beyond their star's death? Would they harness energy from other sources, migrate to other stars, or develop technology to keep their planets warm? Or would they simply accept their fate, living out their final days in a universe that is growing darker and colder? Ultra-red dwarfs are more than just another type of star. They represent the longest-lasting chapter in the history of the cosmos, a final stand against the inevitable heat death of the universe. They remind us that the universe is not just shaped by dramatic explosions and cataclysmic events, but also by the slow, steady persistence of the smallest and dimmest objects. And if we are lucky, one day we may find that we are not alone in this vast expanse. That somewhere, orbiting one of these ancient, slow-burning stars, another civilization has been watching the cosmos unfold for longer than we can even comprehend. Perhaps they already know the answers we seek. Perhaps they have already solved the mysteries we struggle to understand. But for now, the mystery remains. The ultra-red dwarfs continue to burn, quietly defying time itself. And as we search for answers, they wait, unchanged, unmoving, existing on a scale beyond anything we have ever known. Ultra-red dwarfs challenge the very way we perceive time. Our human experience is shaped by rapid changes. A single century can see the rise and fall of empires, the birth of new technologies, and entire revolutions in thought. But in the realm of ultra-red dwarfs, change is almost non-existent on any humanly comprehensible scale. If we were to observe one of these stars for an entire human lifetime, it would remain virtually identical. No sudden flares of death, no dramatic shifts, just an eternal, unwavering glow. Imagine a civilization evolving under such a star. Without the constant cycle of day and night as we know it, their sense of time might be unrecognizably different. Would they even measure time in years or centuries? Would they see history as we do, with beginnings and endings? Or would they perceive existence as something more continuous, more fluid, without the need for strict demarcations of past, present, and future? This brings us to one of the strangest aspects of ultra-red dwarfs: their sheer potential to outlive everything else in the universe. The Sun, for all its brilliance, will burn out in about 5 billion years. Even larger stars, those that shine the brightest, last only a few million years before collapsing into black holes or neutron stars. But ultra-red dwarfs? They are expected to last for hundreds of trillions, possibly even quadrillions of years. To put that into perspective, the universe itself is only about 13.8 billion years old. That means that even the oldest ultra-red dwarfs we see today are still in their infancy compared to their total lifespan. These stars will still be shining when every other sun-like star has long since burned out. They will still be glowing when galaxies have begun to fade into the darkness of an expanding, cooling universe. And yet, despite their astonishing longevity, we know so little about them. We cannot directly observe an ultra-red dwarf reaching the end of its life because none have ever died yet, not in the entire history of the universe. Their theoretical demise is something that exists only in mathematical predictions, not in actual observation. This means that every assumption we have about them is, in some sense, an educated guess. What if they behave differently than expected? What if, instead of fading into a dark, cold husk, some process keeps them alive even longer? Could there be ultra-red dwarfs that persist far beyond even the currently predicted limits of stellar evolution? If so, what would the universe look like in such a far future? By the time the last ultra-red dwarfs begin to die, galaxies will have long since dispersed. Most stars will be dark remnants, white dwarfs cooling into black dwarfs, neutron stars silently drifting, black holes slowly evaporating. The universe will be unrecognizably different from what we see today. Yet these stars, the smallest and faintest of all, will still endure. They will be the last sources of warmth, the last beacons of light in a cosmos that is otherwise plunging toward absolute zero. If any form of life exists by then, it will not be in bright, thriving galaxies but in the feeble glow of these tiny, ancient stars. And here's where things get even stranger. If ultra-red dwarfs can last for trillions of years, could intelligent life around them also last that long? Could there be civilizations that do not rise and fall in mere millennia, but instead persist for billions or even trillions of years? Would such a civilization look anything like ours, or would they have evolved to be something else entirely, something adapted to the unchanging, eternal nature of their environment? It's possible that the key to understanding long-term survival in the universe is not found in the dramatic, fast-burning civilizations we imagine, but in slow, patient forms of life that barely seem to change. Maybe the civilizations that endure are not those that expand aggressively or seek conquest, but those that have mastered the art of quiet persistence, adapting to the rhythms of a star that does not burn out. And if such a civilization exists, how would they view us? Would we seem like flickering candles, here for a brief moment before vanishing into history? Would they see our technological revolutions as little more than bursts of flame, burning hot but fleeting? Would they even recognize us as intelligent, or would we seem too short-lived, too chaotic, to be worth understanding? Perhaps they have already seen civilizations like ours before, thousands, maybe millions of them, each one emerging, reaching for the stars, then fading away while they remain unchanged. If ultra-red dwarfs are the long-term survivors of the universe, then any life that arises around them might also be built for survival on an entirely different scale. They might witness the rise and fall of countless alien empires, watching from a distance as species come and go, leaving behind only relics in the dust. This presents an unsettling thought. If the most long-lived stars also host the longest-lived civilizations, then maybe the beings who truly understand the universe are not the ones burning brightly and vanishing quickly, but the ones who endure in the shadows, watching as everything else fades away. And if they are out there, still watching, still waiting, what might they know that we do not? If such civilizations exist, long-lived, slow-changing, and possibly ancient beyond our comprehension, how would they communicate? Would they even bother reaching out to species like ours, which rise and fall in the blink of an eye from their perspective? To us, 1,000 years is a vast stretch of time. It encompasses entire epochs of human history, from ancient empires to modern technology. But for a civilization orbiting an ultra-red dwarf, 1,000 years might be nothing more than a fleeting moment. If their sense of time is stretched across millions or billions of years, then their methods of communication might reflect that. Imagine an alien species that sends messages at an excruciatingly slow pace, perhaps one word every 1,000 years. To them, this might be a normal rate of conversation, the equivalent of how we exchange sentences in real time. But to us, it would be imperceptible, completely outside our ability to recognize as communication. If such a species were trying to send a signal to us right now, we might not even realize it. This raises a disturbing possibility. What if the universe is already teeming with communication, but it's happening on a timescale that we are simply unable to detect? What if ultra-red dwarf civilizations have been broadcasting messages for millions of years, but their signals are so slow, so drawn out over time, that we don't recognize them as anything but background noise? It's also possible that these civilizations do not use conventional radio signals at all. Perhaps they communicate through gravitational waves, or subtle shifts in the structure of space itself, methods of messaging that we have not yet developed the ability to perceive. Or perhaps they simply do not communicate in ways we would recognize as language. What if their form of knowledge transfer is not through speech or text but through the manipulation of entire planetary environments? Maybe they alter the atmospheres of planets over hundreds of thousands of years as a way of encoding messages for others to decipher. Maybe they shape the orbits of moons, leaving behind patterns only visible to those who think on the same astronomical timescales as they do. If such beings exist, it would make sense that we haven't detected them. They would have no reason to rush, no urgency to shout across the void. Their time is nearly infinite compared to ours, and from their perspective, the civilizations that flare up and burn out quickly, like ours, may not even be worth engaging with. It's even possible that they see us in the same way we see mayflies. These insects live for only a day, while we exist for decades. To them, our lifespan is incomprehensible. Now imagine that same gap, but stretched across millions or billions of years. To a civilization around an ultra-red dwarf, we might be nothing more than ephemeral bursts of activity, too brief to even register as something worth interacting with. And yet, despite all of this, we keep searching. We scan the skies, hoping to find signs of life, believing that someone, somewhere, might be reaching out to us. But what if the ones who are truly waiting, the ones who are truly patient, are not us, but them? What if they have already seen countless civilizations like ours before? What if they have witnessed entire galaxies rise and fall, species evolve and go extinct, and they know something we do not? What if the reason we haven't heard from them is because, from their perspective, we are already gone? If an ultra-red dwarf civilization perceives time in ways we can't comprehend, their entire approach to existence would be different. Their history would not be measured in decades or even centuries, but in millions or billions of years. While human civilizations rise, develop, and collapse within the span of a few thousand years at most, an intelligent species orbiting an ultra-red dwarf would have the luxury of near-eternal stability. With their star remaining unchanged for trillions of years, they might not experience the pressures that drive rapid development and competition. For us, survival has always been a race against time. We live in a universe where change is constant. Our planet undergoes climate shifts, natural disasters strike unpredictably, and our sun will one day expand into a red giant, rendering Earth uninhabitable. These looming threats push us toward innovation, forcing us to develop new technologies, expand our reach, and seek ways to preserve our species. But for a species orbiting an ultra-red dwarf, the urgency we take for granted might not exist at all. If their world is stable for eons, if their environment remains unchanged for what we would consider infinity, then their concept of progress might be completely alien to us. Imagine a civilization that does not experience war because resources are plentiful and unchanging. Imagine a species that does not innovate rapidly because there is no pressure to do so. Would they develop technology at all? Would they see the need for exploration, expansion, or invention? Or would they instead evolve into something more contemplative, more patient, existing in a state of almost meditative stasis, content to simply endure while the rest of the cosmos burns out around them? It is also possible that such a civilization, instead of being slow and unchanging, has reached a level of advancement so far beyond our own that we cannot even comprehend their existence. If their technology has had billions of years to develop, without the interruptions of wars, natural disasters, or environmental collapse, then they may have already solved problems that we are only beginning to consider. They may have achieved a form of post-biological existence, shedding physical forms in favor of something more durable, more suited to the timescales of their star. Perhaps they have uploaded their consciousness into artificial constructs that do not decay. Perhaps they have merged with their planet itself, existing as a kind of planetary intelligence that does not need bodies, cities, or even technology in any form that we would recognize. If this is the case, then we may be surrounded by intelligence that we simply cannot perceive. We search for signs of life based on what we know: radio signals, chemical biosignatures, physical artifacts. But what if the most advanced civilizations have long since moved beyond such crude methods of communication? What if the truly ancient intelligences of the universe exist in ways that are completely invisible to us? Even if they do have physical forms, their approach to the universe might be fundamentally different from ours. For humanity, space travel is difficult because we are bound by the limits of biology. Our lifespans are short, so we need fast travel to reach distant planets within a reasonable time frame. Our bodies are fragile, so we need protective habitats to survive in the vacuum of space. But a species that has evolved under an ultra-red dwarf may have adapted in ways that make space travel far easier for them. If they live for millions of years, then time is not a constraint. They would not need to rush. They could send ships to other stars at incredibly slow speeds, content to wait thousands, or even millions of years for results. Their biology, too, might be adapted for long-duration space travel. Perhaps they do not require oxygen or liquid water. Perhaps they have evolved to survive in extreme cold, making deep space journeys far more manageable. They might not even need traditional spacecraft, instead using their own biology to enter a kind of hibernation, drifting between the stars for eons without concern. And if such beings exist, patient, ancient, and technologically advanced beyond our understanding, then what do they think of us? Do they see us at all? Are they watching us with curiosity, observing how a fast-burning civilization like ours develops? Or do they see us as insignificant, too ephemeral to be worth noticing? It is possible that we have been visited by such beings before, but in ways we do not recognize. If their concept of communication is different from ours, then they may have already left messages for us that we simply cannot comprehend. Perhaps they have altered the orbits of celestial bodies as a form of signal, expecting that any intelligent species would eventually decipher the pattern. Perhaps they have encoded information into cosmic radiation, assuming that any advanced species would eventually learn to read the data. But what if we are simply not advanced enough yet? What if we are still in our infancy, not yet capable of understanding the deeper language of the cosmos? If ultra-red dwarf civilizations are billions of years ahead of us, then their technology may be so advanced that it is indistinguishable from natural phenomena. We might be staring at their messages every day, studying them as unexplained cosmic anomalies, without ever realizing that they are deliberate. And this leads to an even greater question. If the most advanced civilizations in the universe are the ones that last the longest, then are we on the right path? Our civilization is built on rapid change, expansion, and consumption. We deplete resources, create waste, and push ourselves to grow at an unsustainable rate. But what if the true key to survival is not expansion, but longevity? What if the civilizations that endure are not the ones that seek conquest, but the ones that learn to exist in harmony with their environment, stretching their existence across eons instead of centuries? If ultra-red dwarf civilizations have truly unlocked the secret to surviving trillions of years, then perhaps they are not searching for us at all. Perhaps they are waiting for us to reach their level, to evolve beyond our current state, to learn patience, to extend our own lifespans until we can finally perceive reality as they do. Maybe in their eyes, we are still children, too young to understand the universe's true nature. And if that is the case, then what happens when we finally reach their level? Will we be welcomed into a vast, hidden network of ancient intelligences, communicating in ways we had never imagined? Or will we find that the universe, despite its infinite potential, is ultimately silent, not because there is no one out there, but because the ones who endure have long since stopped speaking to those who burn out too quickly to matter? If the universe is truly filled with ancient, slow-moving civilizations orbiting ultra-red dwarf stars, then what kind of structures or megaprojects might they build? While humanity dreams of massive space stations, Dyson spheres, and interstellar colonies, a species that thinks on billion-year timescales might create something even stranger, something that does not look like technology at all. What if the largest artificial structures in the universe are not massive metal constructs, but planetary or even stellar-scale modifications that we mistake for natural phenomena? We assume that an advanced civilization would build something recognizable to us, something that emits heat, gives off artificial signals, or moves in a way that defies natural physics. But what if they build in a way that is indistinguishable from nature itself? Imagine a civilization that has had billions of years to shape its world to perfection. Instead of constructing artificial habitats, they might have transformed their entire planet into a vast, self-sustaining organism, an ecosystem designed not just for survival, but for comfort and efficiency on a scale we cannot imagine. Their forests might be artificial yet indistinguishable from natural ones, engineered to provide food, energy, and even information processing at a planetary level. Their oceans might not just be water, but complex biological networks that function as computing systems, storing their knowledge in the patterns of currents and waves. Or what if they have taken their modifications even further, altering their star itself? An ultra-red dwarf civilization might eventually reach a point where they do not just live near their star, but actively control its energy output, using subtle gravitational manipulations to extend its life even further, ensuring their home remains habitable for trillions of years. Instead of burning out, their star could be carefully regulated, with its energy output adjusted to fit their needs. To us, it would look like an ordinary red dwarf, unchanging, quiet, and seemingly natural, but in reality, it could be an artificial construct on a scale beyond our comprehension. And what if they are not even bound to a single location? With so much time at their disposal, an ultra-red dwarf civilization could spread across the galaxy without us ever noticing. Unlike humans, who seek rapid expansion and colonization, they might expand so slowly that it appears invisible to us. Over millions of years, they could send small, self-replicating probes to other star systems, carefully terraforming planets at an imperceptibly slow rate, preparing them for life in a process that takes eons. If they do this carefully enough, their influence could be everywhere, entire regions of space subtly shaped by their technology, yet to us, it would look completely natural. If they have truly achieved mastery over time, then they may not even perceive space travel the way we do. Instead of launching massive ships at high speeds, they might simply wait for the natural drift of stars to bring new worlds into reach. Over millions of years, even distant stars shift positions, and a civilization with patience beyond our understanding might use these slow movements to spread without ever needing high-speed travel. They could let entire solar systems move toward each other, colonizing new worlds at a rate that seems absurdly slow to us, but is completely reasonable for them. And if they exist, watching, waiting, perhaps even subtly shaping the universe around us, then why have we never detected them? One possibility is that they deliberately avoid interaction with younger civilizations. If their survival depends on stability and patience, then they might see rapid, aggressive species like ours as threats, civilizations that burn brightly for a short time before destroying themselves. They may have seen countless species like us before, rising quickly, consuming resources, and then vanishing in a cosmic blink of an eye. If they have learned from history, they may have decided that the safest strategy is to remain hidden, avoiding contact with civilizations until they prove themselves capable of long-term survival. Or perhaps they do not hide at all, Perhaps we simply lack the ability to see them. If their technology is truly advanced, then it may no longer emit detectable energy in the way we expect. Our search for extraterrestrial intelligence is based on the assumption that alien civilizations will use electromagnetic signals like radio waves. But what if an ultra-red dwarf civilization has moved beyond such primitive forms of communication? If they communicate through quantum entanglement, gravitational waves, or even methods that manipulate space-time itself, then we would have no way of detecting their presence. It is also possible that we have already encountered the remnants of such civilizations without realizing it. If they have been around for billions of years, then some may have already gone extinct, leaving behind artifacts that we mistake for natural structures. Some of the strangest objects in the universe, unexplained anomalies, peculiar planetary formations, or even oddly behaving stars, could be the remnants of ancient projects built by ultra-red dwarf civilizations long ago. Perhaps some of the planets we consider dead were once thriving civilizations that lived for eons before vanishing. Perhaps some of the moons and asteroids we see are not natural at all, but artificial structures so old and eroded that they now appear indistinguishable from rock. If a civilization existed for 1 billion years and then disappeared, its technology would not look like the futuristic cities we imagine. It would look like ruins buried so deep in time that they are no longer recognizable as artificial. And if the longest-lived civilizations are the ones that survive by staying hidden, then maybe the universe is not empty at all. Maybe it is filled with ancient intelligences that have simply learned the ultimate lesson of survival: to watch in silence, to exist without drawing attention, and to wait for others to either destroy themselves or evolve into something capable of understanding them. So the real question is not whether they are out there, but whether we will ever reach the point where we can perceive them. Will we become one of the fleeting civilizations that burns out too quickly to matter, or will we learn to think like they do, to slow down, to extend our existence, to stop seeing time as an enemy and start seeing it as the key to survival? And if we do, will they finally reveal themselves? Or will we simply join them in silence, waiting for the next species to rise, watching as the cycle repeats for another 1 trillion years? If ultra-red dwarf civilizations do exist, the implications stretch far beyond just their survival. Their presence would mean that the universe is not only filled with intelligent life but also shaped by it, subtly, invisibly, and perhaps in ways that defy our ability to comprehend. It would mean that intelligence is not a brief spark but an enduring phenomenon, one that can last longer than stars themselves. And if that is true, then everything we think we know about the fate of civilizations, about progress, about expansion, about technology, could be completely wrong. We assume that the future belongs to those who conquer, to those who spread rapidly, to those who push the limits of physics and engineering. But what if the real winners of the cosmic game are those who slow down? Those who do not chase power but instead master patience? For a civilization living around an ultra-red dwarf star, the goal may not be expansion at all. Instead of reaching out, they may seek to perfect their home. Instead of consuming resources, they may have learned to recycle everything with perfect efficiency. Instead of pursuing energy-intensive technologies, they may have developed methods of survival that require almost nothing at all, allowing them to live in near-total equilibrium with their star, making them almost invisible to outside observers. This raises an unsettling question: what if the natural state of advanced civilizations is not growth, but stillness? What if the reason we do not see intelligent life in the universe is because the most successful civilizations are the ones that stop moving, stop consuming, and stop signaling? It is possible that these civilizations have reached what some theorists call the asymptotic limit of technological advancement, the point at which there are no more meaningful innovations left to make, because everything that can be optimized has already been perfected. If they have reached that stage, then there is no need for constant invention, no need for wasteful expansion, no need for war or conflict. They could live in a state of near-permanent stability, existing in a way that is nearly indistinguishable from nature itself. And if they have achieved this, then they would not be sending out radio signals. They would not be launching starships. They would not be building massive, energy-hungry megastructures. They would not even look like a civilization to us. They would look like nothing at all. This might explain one of the greatest mysteries in astrophysics, the strange behavior of some ultra-cool, ultra-long-lived stars. Astronomers have noticed that some red dwarfs exhibit odd fluctuations in brightness, strange patterns of energy output that do not match standard stellar models. These anomalies are usually dismissed as quirks of stellar physics. But what if they are not natural at all? What if they are signs of artificial regulation, signs that something is controlling the flow of energy, keeping the star at exactly the right conditions for life to persist? If so, then it would mean that the oldest civilizations in the universe are not only still alive but are actively maintaining their worlds in a way that we cannot yet understand. It would mean that the most advanced beings in the cosmos have achieved the ultimate goal, the ability to exist indefinitely, never threatened by resource scarcity, never needing to expand or fight, never worried about extinction. And if that is true, then the lesson for humanity is clear. Our survival will not be determined by how fast we expand or how much power we acquire. It will be determined by whether we learn to adapt to time itself, whether we learn to slow down, to exist sustainably, to master the patience of the ultra-red dwarf civilizations that may already be watching us, waiting to see if we will destroy ourselves or if we will finally understand the true path to survival. If they are out there, they are not just aliens. They are time travelers in a sense, beings who have learned to ride the slowest currents of the cosmos, existing in a state of quiet equilibrium, surviving long after more reckless species have vanished. They are the ultimate survivors, the last intelligences left standing when the rest of the universe has burned itself out. And one day, if we last long enough, we might meet them. Not in a grand first contact moment, not with flashing lights and alien ships descending from the sky, but in the slow realization that we are not alone, that we never were. That they have been there all along, waiting in the dark, patient as the stars themselves. Ultra-red dwarf stars may be the key to understanding not just the survival of alien civilizations, but the long-term future of life itself. Unlike larger stars, which burn out relatively quickly, ultra-red dwarfs can last for trillions of years, longer than the current age of the universe. This means that if life ever formed around one of these stars in the distant past, it could still be thriving today, evolving in ways that are completely beyond our comprehension. But the nature of these stars creates strange and extreme conditions that challenge our understanding of habitability. Ultra-red dwarfs are incredibly dim, meaning that any planet in their habitable zone must be extremely close to the star, sometimes orbiting in just a few days. This proximity causes gravitational forces to lock planets in tidal synchronization, meaning that one side of the planet always faces the star while the other remains in eternal darkness. This leads to a bizarre planetary environment, where one hemisphere experiences constant daylight, while the other remains in an unending frozen night. The temperature difference between the two sides creates violent storms and extreme weather patterns, as winds attempt to redistribute heat across the planet's surface. If life exists in such a place, it would likely be found in the narrow twilight zone between the two extremes, a region of permanent sunset where conditions might be stable enough to support a biosphere. But ultra-red dwarfs are not just dim, they are also highly active, especially in their early years. These stars produce powerful solar flares, releasing bursts of radiation that can strip away planetary atmospheres and make life nearly impossible. Any civilization that developed around an ultra-red dwarf would need to overcome these deadly flares, either by evolving natural defenses, developing advanced shielding technology, or perhaps even altering their star itself to reduce its activity. Some astronomers speculate that planets around these stars could have thick atmospheres or large oceans that help regulate temperature and protect life from radiation. If intelligent beings evolved under such conditions, their entire perception of the universe would be different from ours. They would never experience true night or day, only an unchanging dim glow in the sky. Their concepts of time and change would be shaped by a world where the stars do not rise or set, where the environment remains the same for thousands, or even millions of years. This raises an interesting question. If civilizations can arise in such extreme conditions, how might they differ from those that evolve around more sun-like stars? A species that grows up under an ultra-red dwarf would never know what it is like to see a bright sky. Their entire experience of the cosmos would be shaped by a dim, reddish glow that never changes, a sky without shifting shadows, without seasons, without the cycle of day and night? Would they develop a completely different sense of time? Would they even perceive motion in the same way that we do? And what about their technology? If a civilization arose in an environment of near-total stasis, would they even feel the need to innovate at all? Humans develop technology in response to changing conditions, seasons, natural disasters, resource scarcity. But a species living under an ultra-red dwarf might never face these challenges. Their world might be so stable that technological progress happens at a pace that seems unimaginably slow to us. Instead of rapid bursts of innovation, their advances might unfold over millions of years, making them effectively invisible to outsiders looking for signs of progress. If this is the case, then it could explain why we have never detected signals from such civilizations. We assume that advanced beings will eventually develop powerful technologies and attempt to communicate across the stars. But what if some civilizations never see the need? What if they reach a comfortable equilibrium and remain there indefinitely, living in near-total harmony with their environment, making only the smallest, slowest changes over time? And if ultra-red dwarf civilizations are truly this patient, then they may have already outlived countless other species. They could have watched as faster, more aggressive civilizations rose and fell, burning themselves out in wars or environmental collapse. If they have learned this lesson, then they might have chosen the ultimate survival strategy: to remain unnoticed, avoiding detection, avoiding expansion, existing in a state of quiet endurance while the rest of the universe destroys itself. This would mean that the universe is not empty, but filled with civilizations that have simply mastered the art of long-term survival. They do not conquer. They do not expand. They do not announce their presence. They simply wait, knowing that time is on their side. And in the end, when all the bright, short-lived stars have burned out, they will be the last ones left. If ultra-red dwarf stars are the ultimate long-term survivors of the cosmos, then the civilizations that may exist around them would have developed in ways that defy our understanding of progress, expansion, and even survival itself. Unlike human civilization, which constantly fights against the passage of time, rushing to innovate, expand, and extract resources, any intelligent beings that evolved around an ultra-red dwarf would have been shaped by an entirely different relationship with time. They would not have grown up under a sun that rises and sets, marking the passing of days. They would not have experienced the urgency of seasonal changes forcing rapid adaptation. Instead, they would have lived in a world of near-total stasis, where the glow of their star remains unchanged for billions, even trillions of years. This raises an incredible question: what happens when intelligence evolves under conditions where time almost seems to stand still? Would such beings even develop a concept of urgency? Would they ever feel the need to progress at all? A civilization that never experiences sudden environmental shifts or resource shortages might develop at a pace so slow that it appears stagnant to outsiders. Their version of technological advancement could unfold over hundreds of millions of years, rather than centuries or millennia. To us, such a civilization might appear frozen in time, completely unchanging. But in reality, their progress could be happening on a scale that we simply lack the patience to observe. Just as a mayfly, living for only 24 hours, cannot comprehend the slow growth of a tree over centuries, we might be incapable of perceiving the true nature of ultra-red dwarf civilizations because their actions unfold over epochs beyond our ability to measure. This could be why we have never detected signs of intelligent life in the universe. We expect advanced beings to be sending radio signals, building massive space structures, or colonizing new worlds. But what if the most advanced civilizations do none of these things? What if they have already solved the problem of expansion, realizing that true survival is not about conquering more space, but about making the most of what they already have? If this is the case, then the most successful civilizations might be those that do not seek power, do not consume resources recklessly, and do not attempt to spread beyond their homeworlds. Instead, they would exist in a state of near-perfect balance with their environment, having reached a level of technological sophistication that allows them to sustain themselves indefinitely without any visible outward signs of progress. One possible explanation for this is the idea of technological asymptote, the point at which a civilization has developed everything it needs and no longer has any reason to innovate further. We assume that technological progress is an endless process, but what if there is a point where all problems have been solved? A civilization that has mastered energy efficiency, resource recycling, and environmental stability might reach a stage where there is simply no need for further technological change. If an ultra-red dwarf civilization has reached this stage, then it would mean that their society has become almost invisible, blending so seamlessly with their world that they leave no detectable traces. They would not build enormous structures that emit waste heat. They would not send out artificial signals that could be intercepted by distant observers. They would exist in a way that appears completely natural, making them indistinguishable from their planet's own biological and geological processes. This raises another intriguing possibility. What if we have already found evidence of such civilizations, but simply failed to recognize it? Some ultra-red dwarf planets exhibit strange atmospheric compositions that do not entirely align with what we expect from natural planetary processes. Some have unusual climate patterns, inexplicable levels of heat retention, or even signs of atmospheric regulation that seem oddly precise. These anomalies are usually dismissed as quirks of planetary evolution, but what if they are not? What if they are the signatures of advanced civilizations that have learned how to manipulate their environments in ways that appear completely natural? Imagine a world where every molecule of the atmosphere is carefully managed, where energy flows are precisely controlled to ensure the perfect climate for life. Such a civilization would not need large-scale industrialization, noisy megastructures, or resource-guzzling technologies. Instead, they would operate on a microscopic level, controlling their environment at a scale so fine that it appears indistinguishable from nature itself. This could explain one of the strangest puzzles in astronomy. Why do we see so many planets with conditions that seem almost, but not quite, right for life? Perhaps some of these planets are not just coincidentally habitable. They are actively maintained, shaped by intelligent beings who have mastered the art of planetary engineering. And if that is true, then we are not just looking at random worlds. We are looking at the homes of civilizations that have learned the ultimate secret of survival: how to exist indefinitely without consuming, without expanding, without ever revealing themselves. They are not absent. They are simply patient. Ultra-red dwarf stars are the quiet sentinels of the universe, burning dimly but persistently, outliving all other types of stars. Their immense longevity, trillions of years, means they will be among the last sources of warmth and light when the cosmos reaches its final stages. But despite their endurance, they are shrouded in mystery. These stars are incredibly faint, making them difficult to observe, and their unusual characteristics create some of the strangest planetary environments imaginable. The first major challenge in understanding ultra-red dwarf stars is their size. These stars are at the absolute lower limit of what can be classified as a star. They are only slightly larger than gas giant planets like Jupiter, yet they still produce nuclear fusion, albeit at an extremely slow rate. Because of their small size, their cores are incredibly dense, and their surface temperatures are much cooler than those of larger stars. This gives them their signature red color, and in the case of the coolest among them, their light is so faint that it is barely visible to the human eye. This faintness has a dramatic effect on the planets that orbit them. Because they emit so little energy, the only planets that can maintain liquid water must be located extremely close to the star. In many cases, these planets are so close that their orbits last just a few days. This proximity creates extreme tidal forces, which eventually lead to tidal locking, a situation in which one side of the planet is permanently facing the star while the other remains in eternal darkness. A world under an ultra-red dwarf would therefore be unlike anything we see in our solar system. Instead of a cycle of day and night, the planet would be divided into a blazing hot hemisphere bathed in a constant, dim red light and a frozen dark hemisphere trapped in endless night. In between these extremes lies the twilight zone, a narrow strip where the temperatures might be just right for liquid water to exist. If life exists on such planets, it would likely be found in this thin habitable ring, struggling to adapt to an environment where conditions never change. But even this twilight zone is not necessarily stable. Ultra-red dwarfs are known for their violent flaring activity, especially when they are young. These stars frequently produce massive eruptions of radiation and charged particles, sending waves of destruction across their planetary systems. A planet orbiting an ultra-red dwarf would be exposed to unpredictable and devastating solar storms, which could strip away its atmosphere or sterilize its surface. However, some scientists speculate that life could still persist in such extreme conditions. If a planet has a strong magnetic field, it might be able to deflect much of the incoming radiation. If it has a thick atmosphere or vast oceans, these could provide additional shielding, allowing organisms to survive beneath the surface. In such a scenario, life on an ultra-red dwarf planet would be forced to adapt in ways that are completely alien to us. It might exist in deep caves, using geothermal heat to sustain itself. It might evolve biochemical mechanisms to repair radiation damage almost instantly. Or it might find ways to harness the star's unpredictable energy bursts as a source of power. One of the most intriguing aspects of ultra-red dwarf systems is the possibility that they could host planets with exotic chemical environments. Because these stars burn so slowly, their planets have had more time to undergo complex geological and atmospheric transformations. Over billions of years, unique chemical reactions could produce atmospheres rich in compounds that are rare or non-existent on Earth. Some scientists have suggested that planets around ultra-red dwarfs might have atmospheres dominated by hydrogen, ammonia, or even complex organic molecules that could provide the building blocks for life. Another mystery surrounding ultra-red dwarf stars is their formation and evolution. Unlike larger stars, which go through well-defined stages of stellar life cycles, these tiny stars seem to remain in a stable state for nearly their entire existence. While a sun-like star will eventually expand into a red giant and then collapse into a white dwarf, an ultra-red dwarf will continue burning steadily for trillions of years, never undergoing dramatic transformations. This raises the question, what happens to these stars when they finally exhaust their fuel? Some models predict that ultra-red dwarfs will never become red giants. Instead, they will gradually fade, cooling down over unimaginable timescales until they become black dwarfs, cold, dead remnants of stars that no longer emit any light. However, because the universe is only 13.8 billion years old, no ultra-red dwarf has yet had time to reach this final stage. This means that in all of cosmic history, every ultra-red dwarf that has ever formed is still burning today, quietly persisting while larger stars explode or fade away. If ultra-red dwarf stars are truly the last sources of warmth in the far future of the universe, then any civilizations that arise around them may outlast all others. A civilization that develops under such a star would not need to worry about the eventual death of its sun for trillions of years. While civilizations around sun-like stars would have to evacuate their planets when their stars became red giants, civilizations under ultra-red dwarfs could remain in place, evolving on timescales that dwarf even the history of Earth. And this leads to one of the most mind-bending ideas of all. What if the most advanced civilizations in the universe are not the ones that emerged early, but the ones that have yet to be born? If the most habitable environments are those around ultra-red dwarfs, and if those environments will remain stable for trillions of years, then perhaps the greatest civilizations will not arise until long after all the bright stars have burned out. In this scenario, we are not early explorers in a universe filled with alien empires. We are ancient relics in a cosmos where the true golden age of life is still to come. The civilizations of the distant future may not just outlive us. They may be so different from us that we cannot even begin to imagine their nature. They may evolve in ways that are completely unlike anything seen on Earth, shaped by the strange and extreme conditions of ultra-red dwarf planets. Could it be that the universe is designed not for brief, fleeting bursts of life, but for slow, enduring civilizations that emerge only in the longest-lived environments? If so, then ultra-red dwarf stars are not just curiosities. They are the true engines of the future, the places where life will not just survive, but thrive for untold ages to come. If ultra-red dwarf stars are the ultimate survivors of the universe, then their planetary systems may be the only places where life can persist far into the future. While stars like our Sun will burn brightly for a few billion years before dying in dramatic fashion, ultra-red dwarfs remain stable for trillions of years, providing a continuous energy source long after all other stars have vanished. This raises profound questions about the nature of life, the future of intelligence, and even the fundamental structure of the cosmos itself. One of the biggest mysteries surrounding ultra-red dwarfs is their ability to host habitable planets. Unlike sun-like stars, which have a wide habitable zone where liquid water can exist, ultra-red dwarfs require planets to orbit at extremely close distances to remain warm enough for life. But this close proximity comes with challenges. These planets are almost always tidally locked, meaning one side permanently faces the star while the other remains in darkness. This creates a world of extreme contrasts. One hemisphere is in a state of perpetual daylight, while the other is frozen in eternal night. Yet, despite this harsh environment, life might still find a way to survive. The region between these two extremes, the so-called terminator zone, is where conditions may be just right for liquid water. If an atmosphere exists, winds might redistribute heat, allowing for a narrow strip of habitability across the planet's surface. In such a scenario, life on these worlds would not follow the same patterns as it does on Earth. There would be no traditional day-night cycles, no seasons, and no dynamic weather patterns like those we experience. Instead, the climate would be largely static, with predictable conditions persisting for millions or even billions of years. The impact of stellar flares is another critical factor in determining habitability. Ultra-red dwarfs, particularly in their younger years, are known for their violent stellar activity. They frequently produce massive bursts of radiation, sending streams of charged particles outward at incredible speeds. These flares can be hundreds or even thousands of times more powerful than those seen on our Sun, and they occur with alarming frequency. If a planet is not protected by a strong magnetic field or a thick atmosphere, these outbursts could strip away its air and water, rendering it lifeless. However, some researchers speculate that life might evolve ways to adapt to these extreme conditions. Perhaps life could exist underground, shielded from radiation by layers of rock and soil. Perhaps it could develop biochemical mechanisms that repair radiation damage faster than it occurs. Or perhaps life could even use the flares as an energy source, harnessing the bursts of ultraviolet and X-ray radiation in ways we cannot yet imagine. If such life exists, it would be unlike anything we have ever encountered, resilient, adaptable, and uniquely suited to the extreme conditions of an ultra-red dwarf system. Another intriguing aspect of ultra-red dwarf stars is their sheer longevity. While massive stars burn out in just a few million years and sun-like stars last for about 10 billion years, ultra-red dwarfs will continue shining for trillions of years, orders of magnitude longer than any other type of star. This means that planets orbiting these stars have vastly more time to develop and evolve. On Earth, life took billions of years to go from simple single-celled organisms to complex, intelligent beings. If life around ultra-red dwarfs has trillions of years to evolve, what kinds of creatures might eventually arise? If intelligence does emerge in such a system, it would have no need to worry about the death of its star for an unfathomable amount of time. Unlike civilizations around sun-like stars, which would eventually need to flee their dying star, civilizations in ultra-red dwarf systems could remain in place indefinitely. This raises an astonishing possibility. What if the most advanced civilizations in the universe are not the ones that emerge early, but the ones that evolve slowly over trillions of years under the dim glow of ultra-red dwarfs? In such a scenario, the universe as we know it might be in its infancy. We often think of ourselves as being at the peak of cosmic history, but what if we are actually among the first intelligent species to arise? What if the true golden age of life in the cosmos has not even begun? If ultra-red dwarf planets provide the longest-lasting habitable environments, then the most advanced civilizations might not yet exist. They may emerge billions or even trillions of years from now, long after our own civilization has disappeared. This idea leads to another strange question. Could it be that the nature of the universe itself is biased toward ultra-long-lived systems? The vast majority of stars in the universe are red dwarfs, and the ultra-red dwarfs among them will persist longer than anything else. If the fundamental laws of physics favor environments that last the longest, then perhaps the most important cosmic events are not happening now, but are yet to come. Perhaps intelligence and civilization are not meant to flourish under bright, short-lived stars like our Sun, but in the quiet, dim glow of ultra-red dwarfs. The implications of this are staggering. If life is more likely to arise in ultra-red dwarf systems, then it might follow completely different evolutionary pathways than what we see on Earth. Without day-night cycles, organisms might evolve to function in a state of continuous activity, never needing to rest. Without seasons, life might develop in highly stable ecosystems that persist unchanged for billions of years. And with the extreme conditions of stellar flares, life may evolve unprecedented levels of resilience, making it capable of surviving in environments we would consider completely inhospitable. One of the biggest challenges in studying ultra-red dwarf planets is their extreme faintness. These stars are so dim that they are almost invisible to the naked eye, even when relatively close to Earth. This makes detecting their planets incredibly difficult. The best method we have is the transit method, where we look for tiny dips in a star's brightness as a planet passes in front of it. But because ultra-red dwarfs are so small and faint, these dips are incredibly subtle. It requires highly sensitive instruments and long observation periods to detect them. Despite these difficulties, astronomers have already found several planets orbiting ultra-red dwarfs, and many of them appear to be in the habitable zone. The most famous example is the TRAPPIST-1 system, which contains 7 Earth-sized planets, at least 3 of which may have conditions suitable for life. This discovery has fueled excitement among scientists, as it suggests that potentially habitable planets around ultra-red dwarfs might be far more common than we previously thought. As technology advances, we will gain a better understanding of these worlds. Future space telescopes will allow us to analyze their atmospheres, searching for signs of water, oxygen, or even complex organic molecules. If we find such signatures, it would be one of the most significant discoveries in human history, evidence that life may exist beyond Earth, thriving under the dim glow of an ultra-red dwarf star. But even if we do not find life immediately, the study of ultra-red dwarfs will continue to reshape our understanding of the universe. These stars challenge our assumptions about what makes a planet habitable, what conditions are necessary for life, and even how intelligence might evolve on cosmic timescales. They force us to confront the possibility that our place in the universe is not as central as we once thought, that we may be mere spectators in a cosmos that is only beginning to unfold its deepest mysteries. If the future of life belongs to ultra-red dwarfs, then we are only at the dawn of a story that will be written over the next trillion years. Somewhere, in the quiet corners of the galaxy, under the steady glow of a tiny red sun, the seeds of an unimaginable future may already be taking root. Ultra-red dwarf stars represent not only the longest-lived stars in the universe but also the most enigmatic. Their slow, steady burn defies the expectations we have about stellar evolution, making them the ultimate cosmic survivors. While massive stars explode in brilliant supernovae, leaving behind black holes or neutron stars, ultra-red dwarfs quietly persist, providing stable conditions that could foster life long after most other celestial bodies have burned out. One of the strangest aspects of ultra-red dwarfs is their deep connection to the fate of the universe itself. As galaxies age and massive stars disappear, these tiny stars will remain as the dominant light sources for trillions upon trillions of years. This raises a fascinating question: could the civilizations of the deep future rely entirely on ultra-red dwarfs for energy? Imagine a distant time when the universe is no longer vibrant and full of bright stars, but instead, a realm of faint, slowly cooling ultra-red dwarfs, each one surrounded by planets that have adapted to their dim glow. But what exactly happens as these stars age? Unlike our Sun, which will swell into a red giant before shedding its outer layers, ultra-red dwarfs will simply cool and fade over an almost incomprehensible span of time. Eventually, they will transition into black dwarfs, cold, dark remnants of their former selves. However, this process will take longer than the current age of the universe. In fact, no black dwarfs exist yet because the universe is not old enough for any ultra-red dwarf to have cooled that much. This means that, for all practical purposes, ultra-red dwarfs will outlast everything else we recognize today. Another mystery surrounding these stars is how they interact with their planetary systems over immense timescales. Because they burn so slowly, their habitable zones remain stable for far longer than those of larger stars. This could allow for planetary environments where biological evolution proceeds at an entirely different pace, one that is vastly slower or perhaps even more complex than what we observe on Earth. Given enough time, life in these systems might develop adaptations that are completely alien to anything we have ever considered. But the question remains, do these planets actually have the right conditions to support life? One of the biggest concerns is the presence of strong stellar winds and high-energy radiation, especially in the early stages of an ultra-red dwarf's life. Many of these stars exhibit frequent flaring activity, with violent bursts of X-rays and ultraviolet light that could strip away a planet's atmosphere. This has led some scientists to speculate that while planets around these stars might be common, truly habitable worlds could be far rarer than we expect. However, there is another side to this argument. While young ultra-red dwarfs can be volatile, their activity eventually settles down. Over time, their flares decrease, and they become remarkably stable. This means that even if a planet loses its atmosphere early on, it could potentially regain it through volcanic outgassing or impacts from icy comets. If this happens, then such a planet might become one of the most stable and long-lasting habitable environments in the universe. The potential for life around ultra-red dwarfs also raises questions about how we search for extraterrestrial intelligence. If advanced civilizations prefer ultra-long-lived star systems, then we might be looking in the wrong places. Instead of searching around stars like our Sun, we might need to focus our efforts on the dimmest, least conspicuous stars in the sky, the ones that will still be shining when all others have gone dark. This idea turns the traditional search for alien life on its head. We often assume that the most advanced civilizations would be located around bright, powerful stars. But what if the opposite is true? What if the real technological powerhouses of the universe are hidden in the quietest corners, in the shadows of faint ultra-red dwarfs? These civilizations, if they exist, would have no reason to rush. They would have eternity to explore, expand, and evolve. This also leads to an unsettling thought. If life is more likely to arise around ultra-red dwarfs, why haven't we already detected signs of it? The universe is filled with red dwarfs, and many of them have planets in their habitable zones. So where are all the alien civilizations? Could it be that they are simply not interested in making contact? Or is it possible that their timescales are so different from ours that they do not perceive us as anything more than a fleeting moment in cosmic history? If ultra-red dwarfs are the future of the universe, then the fate of intelligent life may be deeply tied to these stars. As more powerful telescopes come online, we will gain a better understanding of what is happening in these distant star systems. If we find planets with thick atmospheres and stable climates, it would be a strong indication that life could persist around these stars. And if we find signs of artificial activity, strange energy emissions, unusual orbital patterns, or evidence of megastructures, then we may finally have proof that we are not alone. But until then, the mystery remains. Ultra-red dwarf stars defy our expectations, challenging what we think we know about habitable worlds and the long-term prospects of life in the universe. They are the ultimate survivors, outlasting everything else, silently illuminating the dark future of the cosmos. And somewhere, in the vast expanse of time, under the faint glow of a tiny red star, the next great chapter of life in the universe may already be unfolding. The mystery of ultra-red dwarf stars grows even deeper when we consider their extreme environments. These stars are dim, their light barely reaching beyond their immediate surroundings, yet they hold the potential for entire planetary systems that could last trillions of years. This presents an intriguing paradox. While they may be among the most numerous stars in the universe, their faintness makes them difficult to study. Even the closest ultra-red dwarfs are challenging to observe, requiring advanced infrared telescopes to detect their weak emissions. This limitation means that we know far less about them than other types of stars, leaving open many unanswered questions about their structure, evolution, and potential to host life. One of the most fascinating aspects of ultra-red dwarfs is their temperature. Unlike our Sun, which burns at a surface temperature of about 5,500 degrees Celsius, ultra-red dwarfs can have surface temperatures as low as 1,500 degrees Celsius or even lower. This makes them some of the coolest stars in existence, bordering on the classification of brown dwarfs, stellar objects that never quite gained enough mass to ignite full nuclear fusion. Because of their low temperatures, these stars emit most of their light in the infrared spectrum, making them nearly invisible to the naked eye. If you were to stand on a planet orbiting an ultra-red dwarf, the star would appear as a deep red or even dark orange sphere, casting an eerie, dim glow over the landscape. The atmosphere of a planet orbiting one of these stars would also behave differently from what we are used to. The lower energy output of the star means that any habitable planet must be located much closer than Earth is to the Sun. In many cases, these planets are so close that they become tidally locked, meaning that one side always faces the star while the other remains in perpetual darkness. This could create extreme conditions, with one hemisphere experiencing eternal daylight and the other trapped in an unending frozen night. However, the thin twilight region between these two extremes, where the temperature is just right, could provide a stable environment for life to thrive. But how would life adapt to such an environment? If photosynthesis were to develop on these planets, it would have to work under a much dimmer, redshifted spectrum. On Earth, plants absorb blue and red light while reflecting green, but under an ultra-red dwarf, plants might evolve to absorb more infrared light, potentially appearing black or deep purple. Some scientists have even suggested that entirely new biochemical processes could emerge, producing alien vegetation unlike anything we have ever seen. Instead of relying on traditional photosynthesis, organisms might use infrared radiation to drive metabolic reactions, forming ecosystems that are completely unrecognizable to us. Another major factor in determining whether life could exist around these stars is the presence of water. Since ultra-red dwarfs are small and cool, their radiation pressure is weak, meaning that any water present on orbiting planets is less likely to be stripped away by stellar winds. This could make these planets more likely to retain their oceans over time, providing a key ingredient for life. However, water alone is not enough. Stable climates are also essential. While the early stages of an ultra-red dwarf's life are marked by violent stellar activity, their long-term stability means that once conditions settle, they remain steady for billions or even trillions of years. But what happens when we look at the bigger picture? If ultra-red dwarfs last longer than any other type of star, then they will eventually dominate the universe. Over time, larger stars will die out, leaving only small, dim objects like ultra-red dwarfs to provide the last sources of energy in the cosmos. This could mean that the final civilizations to exist in the distant future will have to rely on these faint stars for survival. Some scientists have even speculated that advanced extraterrestrial societies may have already recognized this and migrated toward ultra-red dwarfs, seeking the longest-lasting sources of energy available. This idea leads to a fascinating possibility. What if intelligent life is not only surviving around these stars but actively thriving? If such civilizations exist, they might have developed entirely different technologies to harness the weak light of their stars. Instead of relying on solar power as we do, they could have found ways to extract energy from the slow nuclear reactions occurring within their star, or even from the faint ambient heat that remains in deep space. Such beings would have adapted to a universe where light is scarce and darkness dominates, evolving in ways that are almost impossible for us to imagine. Yet, despite their importance, ultra-red dwarfs remain one of the least understood types of stars. Because they are so faint, our ability to study them is limited by the capabilities of our telescopes. However, with the advent of new infrared observatories, such as the James Webb Space Telescope, we are beginning to peer deeper into these hidden worlds. Already, astronomers have identified numerous exoplanets orbiting red dwarfs, some of which lie within their star's habitable zone. As our technology improves, we may soon discover whether these planets have atmospheres, liquid water, or even signs of life. One of the most exciting aspects of this search is the possibility of detecting biosignatures, chemical markers that indicate the presence of life. On Earth, certain gases, such as oxygen and methane, are strong indicators of biological activity. If we find similar signatures on planets around ultra-red dwarfs, it could be the first evidence that we are not alone in the universe. However, there is always the challenge of false positives. non-biological processes can sometimes produce similar signals, making it difficult to draw definitive conclusions. Another key challenge in studying ultra-red dwarfs is their unpredictability. While some are stable, others experience sudden bursts of energy, known as stellar flares, that can be thousands of times more intense than the light they normally emit. These flares can strip away atmospheres, irradiate planetary surfaces, and disrupt any potential lifeforms that may be developing. This raises a crucial question: could life around ultra-red dwarfs survive these bursts, or would it be wiped out before it ever had a chance to take hold? Some researchers believe that if a planet has a strong enough magnetic field, it could protect itself from these flares, much like Earth's magnetic field shields us from solar storms. Others argue that life could survive deep underground or beneath thick layers of ice, shielding itself from the worst of the radiation. The search for life around ultra-red dwarfs is not just a scientific endeavor, it is a quest to understand our place in the cosmos. If we find that life is common in these systems, it could mean that the universe is teeming with habitable worlds, just waiting to be explored. On the other hand, if we find nothing but barren, lifeless planets, it may suggest that the conditions required for life are far rarer than we hoped. Either way, the implications are profound, forcing us to rethink everything we know about the potential for life beyond Earth. Ultimately, ultra-red dwarf stars are a window into the far future of the universe. As other stars fade away, these tiny, dim stars will remain as the last beacons of light in an ever-darkening cosmos. Whether they hold the key to understanding alien life, the future of interstellar civilizations, or the final fate of the universe itself, one thing is certain: they are among the most important, yet least understood, stars in existence. Ultra-red dwarf stars are more than just dim celestial bodies scattered across the universe. They are potential lifeboats for the far future, possibly harboring worlds where life could exist under conditions vastly different from our own. While their small size and faint glow make them difficult to observe, they hold the key to understanding not only the evolution of planetary systems, but also the distant fate of the cosmos itself. These stars are like cosmic embers, burning slowly and steadily while the rest of the universe fades into darkness. One of the most intriguing aspects of ultra-red dwarfs is their lifespan. Unlike larger stars, which burn through their nuclear fuel in a matter of millions or billions of years, ultra-red dwarfs can theoretically last for trillions of years, longer than the current age of the universe itself. This is due to their slow rate of nuclear fusion, which allows them to conserve their fuel far more efficiently than stars like our Sun. The implications of this are staggering. If life were to develop around an ultra-red dwarf, it could persist for an unimaginable length of time, evolving in ways we cannot yet comprehend. This means that while life on Earth may eventually come to an end, somewhere out there, in the light of an ultra-red dwarf, life could continue long after our own civilization has vanished. Another remarkable trait of these stars is their stability. After an initially turbulent phase of strong magnetic activity and stellar flares, ultra-red dwarfs eventually settle into a period of extreme longevity. This means that, for planets orbiting these stars, conditions could remain relatively stable for billions or even trillions of years. This contrasts sharply with the fate of planets orbiting larger stars, which will eventually expand into red giants and destroy any inner planets before collapsing into white dwarfs. Planets around ultra-red dwarfs, however, could experience a much gentler, more predictable cosmic existence. But what about their habitability? One of the biggest challenges for life around ultra-red dwarfs is the fact that their habitable zones, the regions where liquid water can exist, are incredibly close to the star. Because these stars are so cool, a planet must orbit much nearer than Earth does to receive enough warmth. This leads to several potential problems. First, the planet is likely to be tidally locked, meaning that one side always faces the star while the other is in permanent darkness. This could create extreme temperature differences, with one hemisphere scorching hot and the other freezing cold. However, a thick atmosphere or strong ocean currents could help distribute heat, creating a habitable zone in the twilight region between the two extremes. Another major challenge is the activity of young ultra-red dwarfs. When these stars are young, they are highly active, frequently emitting powerful flares and bursts of radiation. These flares could strip away the atmospheres of nearby planets, making it difficult for life to take hold. However, if a planet forms with a strong enough magnetic field, or if it has an atmosphere rich in protective compounds like ozone, it might be able to withstand these flares long enough for the star to calm down. Once an ultra-red dwarf settles into its stable phase, it becomes one of the safest places in the universe for a planet to exist. Given these factors, astronomers are intensely interested in studying planets around ultra-red dwarfs. With modern telescopes, such as the James Webb Space Telescope, we are now beginning to detect atmospheres on planets orbiting these dim stars. By analyzing the light that passes through a planet's atmosphere, scientists can search for chemical signatures that indicate the presence of water, oxygen, or even potential biosignatures like methane. The discovery of such signals would be one of the most groundbreaking moments in the history of science, providing the first strong evidence that life exists beyond Earth. However, the potential for life around ultra-red dwarfs extends beyond biology. It also raises fascinating questions about the future of intelligence and civilization. If advanced extraterrestrial societies exist, they may have already recognized the immense longevity of these stars and chosen to settle around them. In a universe where most stars will eventually die out, ultra-red dwarfs may be the ultimate refuges for civilizations looking to survive for eons. Some scientists have even speculated that highly advanced species might have engineered ways to harness the weak but steady energy output of these stars, ensuring a nearly infinite power supply. This idea ties into the broader question of the Fermi paradox, the mystery of why we have not yet detected signs of intelligent extraterrestrial life. If ultra-red dwarfs provide such stable environments, then it is possible that civilizations capable of space travel would prioritize settling around these stars rather than larger, shorter-lived stars like our Sun. This could mean that intelligent life is not absent from the universe but rather concentrated around ultra-red dwarfs, hidden from our view due to their faint light. Beyond the search for life, ultra-red dwarfs also play a crucial role in the evolution of the universe itself. As larger stars burn out and fade away, the universe will eventually become dominated by smaller, dimmer objects like ultra-red dwarfs. In the far future, when even the last white dwarfs have cooled into black dwarfs, these tiny stars will be the last remaining sources of light and heat. This means that long after the Milky Way has changed beyond recognition, long after our own Sun has disappeared, ultra-red dwarfs will continue to glow, keeping the last embers of the universe alive. The prospect of these long-lived stars also raises a profound question. If intelligent life is capable of surviving for trillions of years, what would their civilizations look like? Would they exist in a completely different form from anything we can imagine? Would they have found ways to extract energy from their tiny stars with perfect efficiency? Would they have migrated to artificial structures, orbiting these stars in vast, engineered megastructures to maximize their use of every last bit of energy? If such civilizations exist, they would have had more than enough time to develop technologies far beyond our comprehension. Ultimately, ultra-red dwarf stars challenge us to rethink everything we know about the nature of life, civilization, and the long-term future of the universe. They may hold the answers to some of the biggest mysteries in astrophysics, from the conditions needed for life to the potential for civilizations to endure for cosmic timescales. As our ability to study these stars improves, we may soon unlock secrets that redefine our understanding of the cosmos and our place within it. The importance of ultra-red dwarf stars extends beyond their role in cosmic longevity. These tiny, enduring stars could be key to understanding how planetary systems form, evolve, and potentially sustain life under radically different conditions than those seen around Sun-like stars. Because they are so faint and cool, their planetary systems are often compact, with planets orbiting much closer than what we see in our own solar system. This unique arrangement leads to fascinating dynamical interactions, tidal locking effects, and atmospheric evolution that challenge many of our current models of habitability. One of the most intriguing aspects of ultra-red dwarf planetary systems is the high frequency of rocky, Earth-sized exoplanets within their habitable zones. Statistical studies suggest that most of these stars host at least one planet, and many have multiple planets orbiting in tight, resonant chains. This means that in an ultra-red dwarf system, An observer standing on one planet might see other planets in the sky appearing much larger than our own moon. The gravitational interactions between these planets can create complex orbital dynamics, leading to variations in climate and even the potential for exotic atmospheric effects. A major challenge for planets around ultra-red dwarfs is the strong stellar winds and radiation that these stars emit, particularly in their youth. While a planet in the habitable zone of an ultra-red dwarf is positioned close enough to receive sufficient warmth, it is also close enough to be heavily bombarded by high-energy particles. This can strip away atmospheres over time, unless the planet has a strong enough magnetic field to protect itself. Some researchers have proposed that a deep, global ocean or a thick, high-pressure atmosphere could provide a natural shield against these forces, potentially allowing life to persist even in extreme conditions. The question of whether life could exist on such planets is one of the biggest mysteries in astrobiology. On Earth, life is deeply dependent on the sun's energy, but around an ultra-red dwarf, the situation would be very different. The lower energy output and redder light spectrum of these stars mean that photosynthesis, if it occurs at all, would have to adapt to a much dimmer environment. Some scientists speculate that plant-like organisms on such planets might appear black or dark purple, as they would need to absorb a wider range of wavelengths to efficiently capture the limited light available. Other theories suggest that alternative biochemistries could emerge, possibly relying on geothermal energy rather than stellar radiation as their primary energy source. Another factor that makes ultra-red dwarfs fascinating is their role in the ultimate fate of the universe. As larger stars exhaust their fuel and fade into white dwarfs, neutron stars, and black holes, ultra-red dwarfs will continue burning steadily, providing the last flickering lights in a universe that is slowly growing cold and dark. In the far distant future, when even galaxies have dispersed into isolated stars drifting through an expanding void, these tiny stars will remain as the last active objects capable of supporting life. Some theorists suggest that, if any advanced civilization survives into this distant era, they may migrate toward ultra-red dwarfs to extend their existence as long as possible. The potential for long-lived civilizations orbiting ultra-red dwarfs is a particularly intriguing idea. If intelligent life has arisen around such stars, it could have existed for an incomprehensibly long time, refining its technology and knowledge far beyond anything we can imagine. Unlike human civilization, which has only been around for a fraction of a cosmic second, a civilization based around an ultra-red dwarf could persist for billions, if not trillions, of years. What would such beings look like? Would they have developed technologies so advanced that they appear indistinguishable from magic to us? Could they have constructed artificial megastructures around their stars to capture every last bit of energy output? If so, detecting these structures might be one of the best ways to find evidence of extraterrestrial intelligence. The search for planets around ultra-red dwarfs is still in its early stages, but with advancements in telescopes and observational techniques, we are beginning to uncover new worlds at an unprecedented rate. The James Webb Space Telescope has already identified promising candidates for further study, and future missions will focus on directly imaging these planets and analyzing their atmospheres for signs of habitability, or even life. Some researchers are even developing methods to search for artificial signals, such as unusual infrared emissions that might indicate advanced technology harnessing the energy of an ultra-red dwarf. In addition to their potential for habitability, ultra-red dwarfs also challenge many of our assumptions about how stars work. Unlike larger stars, which eventually expand into red giants and eject their outer layers, ultra-red dwarfs never undergo this transformation. Instead, they burn so slowly that they will remain in a steady state for the vast majority of their lifespans. This means that, for any civilizations orbiting these stars, the concept of stellar death might be completely foreign. While humanity must face the reality that our sun will eventually die, a civilization around an ultra-red dwarf would never experience such an event within their timescales of existence. Beyond the mysteries of life and longevity, ultra-red dwarfs also raise fascinating questions about dark matter and the fundamental nature of the universe. Some researchers have proposed that these stars could serve as natural laboratories for testing theories of exotic physics. Because they are so small and cool, they may interact differently with dark matter, potentially allowing us to probe the properties of this mysterious substance that makes up most of the universe's mass. Additionally, their slow-burning nature could help refine our understanding of nuclear fusion and energy generation, providing new insights into how matter behaves under extreme conditions. Despite their small size, ultra-red dwarfs could hold some of the biggest answers to questions that have puzzled scientists for centuries. They may teach us about the limits of habitability, the potential for long-lived civilizations, and even the ultimate fate of the cosmos. With each new discovery, we move closer to understanding these enigmatic stars, and perhaps one day, we will find definitive proof that life exists beyond Earth, thriving in the dim glow of a star so small and faint that it was once thought incapable of supporting anything at all. The study of ultra-red dwarf stars is not just about finding planets or understanding how stars work, it's about redefining the very limits of our knowledge regarding habitability, cosmic longevity, and the hidden mechanics of the universe. These tiny, unassuming stars may hold the key to some of the most profound mysteries of space, from the origins of life to the ultimate fate of the cosmos. And yet, despite their vast importance, ultra-red dwarfs remain some of the most difficult stars to observe. Their faintness makes them almost invisible to the naked eye, even when they are among the closest stars to Earth. This raises the question, just how many of these stars exist, hidden in the vast darkness of space? Astronomers estimate that ultra-red dwarfs are the most common type of star in the universe, vastly outnumbering sun-like stars. Because they shine so weakly, they can easily go undetected even in relatively close proximity to our own solar system. In fact, before the advent of infrared telescopes and high-sensitivity surveys, many of these stars remained undiscovered, even when they were only a few light-years away. The realization that we are surrounded by an invisible majority of stars has reshaped our understanding of galactic structure, revealing that the universe is far more densely packed with these cool, dim objects than previously thought. One of the most remarkable aspects of ultra-red dwarfs is their stability. Unlike larger, more massive stars, which undergo dramatic changes over their lifetimes, ultra-red dwarfs remain relatively constant. They do not experience the violent fluctuations in brightness that are common in larger stars, nor do they go through catastrophic phases like supernovae. This extreme stability could be a crucial factor in supporting life over long timescales. If a planet forms within the habitable zone of an ultra-red dwarf and manages to retain its atmosphere, it could remain in a stable, life-sustaining environment for billions, even trillions, of years. However, stability does not mean these stars are completely quiet. Young ultra-red dwarfs can be surprisingly active, frequently emitting powerful flares that release bursts of radiation far stronger than those seen on our Sun. These flares, which result from intense magnetic activity, can be both a blessing and a curse for any planets in orbit. On one hand, they may help drive chemical reactions that could lead to the formation of complex organic molecules, potentially kickstarting life. On the other hand, they could also strip away atmospheres and expose planets to harmful radiation. The interplay between these effects remains an open question, and astronomers are working to determine whether planets in these systems can develop protective mechanisms, such as strong magnetic fields or thick atmospheres, to withstand the storms of their parent star. One of the biggest challenges in studying ultra-red dwarf planets is determining their atmospheres. Unlike larger, brighter stars, which allow for easier analysis of planetary transits, ultra-red dwarfs require highly sensitive instruments to detect the tiny changes in light when a planet passes in front of them. The James Webb Space Telescope is expected to revolutionize this field by providing high-resolution data on exoplanet atmospheres, allowing scientists to search for signs of habitability, or even biological activity. If we detect oxygen, methane, or other biosignatures in the atmosphere of an ultra-red dwarf planet, it would be one of the most groundbreaking discoveries in history. Another mystery surrounding ultra-red dwarfs is their formation. Traditional models of star formation suggest that the smallest stars should be less common than medium-sized stars, yet observational data shows the opposite. Ultra-red dwarfs are the dominant type of star in the universe. This suggests that the process of star formation may be biased toward creating low-mass stars rather than more massive ones. But why? Some theories propose that dense molecular clouds, which give birth to stars, fragment in a way that naturally favors the formation of smaller objects. Others suggest that ultra-red dwarfs may form in binary or multiple star systems and later be ejected, leaving them to wander the galaxy alone. Understanding this process could provide new insights into how galaxies evolve and how the earliest stars in the universe were born. Perhaps one of the most speculative but fascinating ideas about ultra-red dwarfs is their potential to serve as the final refuges for life in the distant future. As the universe continues to expand and cool, most stars will burn out and fade away. Larger stars will die in spectacular explosions, while even small sun-like stars will eventually exhaust their fuel and become cold, dark remnants. But ultra-red dwarfs will continue to shine. In a future where most of the universe has gone dark, these tiny stars could be the last beacons of warmth and light, offering a safe haven for any civilizations that manage to endure through the cosmic decline. Could advanced civilizations already be migrating toward ultra-red dwarfs in preparation for this far-off future? If intelligent beings have been around for billions of years, far longer than humanity, then they may have already recognized the unique longevity of these stars and chosen to settle around them. Some theorists have even proposed that we should be looking for signs of extraterrestrial intelligence around ultra-red dwarfs, as they might be prime locations for long-term survival strategies. If an alien species has developed technology to harness the energy of these stars efficiently, we might detect their presence through unusual infrared emissions, orbital megastructures, or other technological signatures. Despite their small size, ultra-red dwarfs could play a massive role in shaping the future of astronomy, astrobiology, and cosmology. They challenge our understanding of star formation, planetary habitability, and even the long-term prospects for life in the universe. Every new discovery about these tiny stars brings us closer to answering some of the biggest questions in science. Are we alone? How long can life persist in the cosmos? And what will the universe look like when all the larger stars have faded away? As we continue to peer into the depths of space with ever more powerful telescopes, the secrets of ultra-red dwarfs will become clearer. These stars may not shine brightly in the night sky, but their importance is undeniable. They could be the keepers of life, the architects of long-lived civilizations, and the last surviving witnesses to the end of time itself. In the silent corners of the universe, where light is scarce and time stretches endlessly, ultra-red dwarfs continue their quiet, steady glow, holding within them the answers to some of the greatest cosmic mysteries we have yet to solve. Ultra-red dwarfs defy conventional expectations in almost every way. Their sheer abundance, extreme longevity, and mysterious formation processes make them some of the most fascinating objects in the cosmos. But despite their importance, these stars remain incredibly difficult to study. Their faintness means they can easily blend into the background of space, hiding in the shadows of brighter celestial bodies. Even with advanced infrared telescopes, detecting them requires meticulous observation, and understanding their full nature is still a work in progress. This raises one of the most intriguing questions: how many ultra-red dwarfs are out there, waiting to be discovered? The best estimates suggest that ultra-red dwarfs make up the vast majority of all stars, potentially as much as 70 to 80% of the total stellar population. Yet, paradoxically, they contribute very little to the overall brightness of the universe. If we were to look at the Milky Way from a distant galaxy, the combined light of all these stars would be almost negligible compared to the glow of larger, hotter stars. This has led some astronomers to speculate that our current models of galactic structure might be incomplete. If ultra-red dwarfs are more numerous than we think, entire regions of the cosmos could be packed with stars that are essentially invisible to traditional telescopes. This would not only change our understanding of how galaxies form and evolve, but could also mean that we are missing vast numbers of potentially habitable planets. One of the most puzzling aspects of ultra-red dwarfs is their slow rate of nuclear fusion. Unlike our Sun, which burns through its hydrogen supply relatively quickly, ultra-red dwarfs consume their fuel at an incredibly slow pace. This means they can last for trillions of years, far longer than the current age of the universe. To put this into perspective, no ultra-red dwarf has ever reached the end of its life yet because the universe itself is not old enough for one to have fully run out of fuel. This makes them unique among all known stars, as they provide a glimpse into a future that no other stellar class can show us. If our universe survives for long enough, ultra-red dwarfs will become the dominant sources of light and heat, outlasting all other stars. But what happens when an ultra-red dwarf finally reaches the end of its life? Since no known ultra-red dwarf has yet died, astronomers can only speculate. Unlike more massive stars, which end their lives in dramatic explosions or as white dwarfs, ultra-red dwarfs are expected to slowly fade away. As they burn through the last of their hydrogen, they will gradually become cooler and fainter until they eventually transform into theoretical objects known as black dwarfs, cold, dark remnants that no longer emit significant heat or light. However, this process is so slow that it will take many trillions of years before even the first black dwarf comes into existence. If the universe continues expanding indefinitely, ultra-red dwarfs may be the last active stars to exist before all light finally fades away. Their extreme longevity raises another interesting question. Could intelligent life find a way to survive around these stars indefinitely? In the distant future, when other stars have burned out and galaxies have emptied of usable energy, ultra-red dwarfs might be the final bastions of life. A sufficiently advanced civilization could theoretically migrate to these systems, harnessing the steady, low-energy output of ultra-red dwarfs to maintain their existence for as long as possible. This idea has led some scientists to propose that if extraterrestrial civilizations exist, they may already be clustered around these stars, carefully managing their energy use to maximize their longevity. Searching for signs of such civilizations around ultra-red dwarfs could provide valuable insights into the potential long-term survival of intelligent life in the universe. In addition to their implications for the future, ultra-red dwarfs may also hold answers to some of the deepest questions about the origins of life itself. Because they have stable, long-lived habitable zones, they provide an ideal environment for the slow, gradual processes that might lead to the development of biological complexity. Unlike sun-like stars, which can have relatively short-lived habitable conditions, ultra-red dwarfs offer a nearly constant energy supply over immense timescales. This could mean that any life that emerges on planets around these stars has an unparalleled opportunity to evolve, potentially reaching levels of complexity far beyond what we have seen on Earth. However, there are also challenges to life around ultra-red dwarfs. One major issue is that these stars often exhibit powerful magnetic activity, producing intense stellar flares that can bombard nearby planets with radiation. If a planet is too close to its star, it could lose its atmosphere over time, making it difficult for life to take hold. But recent studies suggest that if a planet has a strong enough magnetic field, it may be able to deflect much of this harmful radiation, allowing it to retain a stable environment. Additionally, thick atmospheres or subsurface oceans could provide natural protection against the harsh conditions of an ultra-red dwarf system. Another mystery surrounding ultra-red dwarfs is their tendency to host tightly packed planetary systems. Because these stars are so small, their habitable zones are located much closer than those of larger stars, leading to the possibility of planets orbiting in extremely compact formations. In some cases, multiple Earth-sized planets can exist in close proximity, potentially allowing for the transfer of organic material between worlds through meteorite impacts. This raises the fascinating possibility that life in ultra-red dwarf systems could be interconnected, with biological material spreading from one planet to another over time. If life is discovered on one planet in such a system, it may be worth investigating whether similar lifeforms exist on its neighboring worlds. Recent discoveries have further highlighted the significance of ultra-red dwarfs in the search for life. Some of the most promising exoplanets ever detected orbit these stars, including those in the TRAPPIST-1 system. This system, located just 40 light-years away, contains at least 7 Earth-sized planets, 3 of which are within the star's habitable zone. The discovery of such a tightly packed, potentially life-supporting system around an ultra-red dwarf has provided astronomers with a tantalizing glimpse of what might be possible elsewhere in the galaxy. If even one of these planets harbors life, it would dramatically reshape our understanding of biology and planetary habitability. But perhaps the greatest mystery of all is the sheer number of ultra-red dwarfs that remain undiscovered. Despite their overwhelming presence in the universe, many of these stars remain completely unknown to us, hidden by their faintness and distance. Some estimates suggest that we have only identified a fraction of the ultra-red dwarfs within our own galaxy, and there could be entire populations of these stars lurking in the depths of intergalactic space. If we could find a way to detect them more easily, we might unlock a vast and unexplored realm of astrophysics, one that could reveal new insights about the evolution of galaxies, the potential for life, and even the fundamental nature of the cosmos itself. As we push the boundaries of astronomical research, ultra-red dwarfs will continue to be a focus of intense study. They may not be the brightest or most spectacular stars, but their significance cannot be overstated. These unassuming objects hold the secrets to the past, present, and future of the universe, acting as cosmic time capsules that preserve information across unimaginable timescales. If we ever hope to understand the full scope of the cosmos, we must pay close attention to these quiet, long-lived stars. They may hold the answers to questions we haven't even thought to ask yet. Ultra-red dwarfs may seem unremarkable at first glance, but their impact on the universe is profound. They exist in numbers that surpass all other types of stars, outlast every other stellar classification, and host some of the most intriguing planetary systems ever discovered. Yet, despite their prevalence, they remain some of the least understood objects in the cosmos. Their faint glow keeps them hidden from view, requiring specialized infrared telescopes to detect them. Even with modern technology, astronomers believe we have only scratched the surface of how many ultra-red dwarfs truly exist. If our estimates are correct, these stars may fill vast regions of space that appear empty to our traditional instruments. What might be lurking in these unseen corners of the galaxy? Could there be entire planetary systems orbiting ultra-red dwarfs, rich with life and activity, yet completely undetectable with our current methods? One of the most perplexing questions about ultra-red dwarfs is their formation. Unlike massive stars, which form in turbulent, short-lived bursts of star formation, ultra-red dwarfs appear to develop at a slow and steady rate. Their low mass means that they require far less material to form than larger stars, allowing them to emerge in environments where other stars might struggle to take shape. Some theories suggest that ultra-red dwarfs could even form in intergalactic space, drifting alone in the void between galaxies, completely isolated from any stellar neighbors. If this is true, then there could be countless ultra-red dwarfs hiding in the darkness between galaxies, waiting to be discovered. Because they burn their fuel so efficiently, ultra-red dwarfs experience an evolution unlike any other star type. More massive stars expand and contract as they burn through their hydrogen, eventually becoming red giants, white dwarfs, or supernovae. But ultra-red dwarfs remain relatively unchanged for nearly their entire existence. Their steady, low-energy fusion process means that they do not fluctuate wildly in brightness or size. Instead, they maintain a stable output for trillions of years. This consistency is one of the reasons why they are considered ideal candidates for habitable planets. Unlike our Sun, which will eventually expand and destroy Earth, ultra-red dwarfs can support planetary systems with relatively little change for an almost incomprehensible amount of time. However, this stability also comes with a trade-off. Because ultra-red dwarfs are so dim, their habitable zones are extremely close to the star itself. Any planet within this zone would experience very different conditions compared to Earth. One of the biggest challenges is the possibility of tidal locking. When a planet orbits so close to its star, gravitational forces can cause one side of the planet to permanently face the star while the other remains in eternal darkness. This could create extreme temperature differences, with one hemisphere burning under constant daylight, while the other freezes in perpetual night. However, some models suggest that thick atmospheres or strong ocean currents could help distribute heat more evenly, potentially making such planets more hospitable than they might initially appear. Another major challenge is the violent nature of young ultra-red dwarfs. Despite their small size and low energy output, these stars can be highly active in their early stages. They frequently emit powerful stellar flares, releasing intense bursts of radiation that could strip away planetary atmospheres or make the surface conditions extremely hazardous. If life were to develop on a planet in such a system, it would need to be highly resistant to radiation or exist underground, beneath thick layers of rock or ice that could shield it from the harsh stellar environment. Some scientists speculate that life could thrive in subsurface oceans, similar to those found beneath the icy shells of moons like Europa or Enceladus in our own solar system. Despite these challenges, ultra-red dwarfs remain one of the most promising places to search for extraterrestrial life. The sheer number of these stars means that even if only a small fraction of them host habitable planets, the total number of potentially life-bearing worlds could be immense. Some researchers argue that life may be far more common around ultra-red dwarfs than around sun-like stars, simply because there are so many more opportunities for it to arise. If this is true, then the best place to look for alien civilizations may not be around stars like our own, but around these small, dim, and ancient celestial bodies. The discovery of the TRAPPIST-1 system has only intensified interest in ultra-red dwarfs. This system, with its 7 Earth-sized planets orbiting a single ultra-red dwarf, has challenged previous assumptions about what kinds of planetary systems can exist. The fact that so many planets can form around such a small star suggests that our understanding of planet formation may need to be revised. If TRAPPIST-1 is not an anomaly but rather a common type of system, then there may be countless similar arrangements scattered throughout the galaxy, each with its own set of Earth-like worlds waiting to be explored. The implications of this are staggering. If ultra-red dwarfs are the most common stars, and if they frequently host tightly packed planetary systems, then the number of potentially habitable planets in the universe could be far greater than we ever imagined. This raises profound questions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. If life is abundant around ultra-red dwarfs, then why have we not yet detected signs of it? Could it be that intelligent life around these stars develops differently? Perhaps civilizations that arise in such environments have no need for the kinds of technology we expect to find. Or maybe they are so well adapted to their stable conditions that they see no reason to expand beyond their homeworlds. As we develop more advanced telescopes, the study of ultra-red dwarfs will become increasingly important. Upcoming missions, such as the James Webb Space Telescope and other next-generation observatories, are designed to detect the faint signals of atmospheres around exoplanets orbiting these stars. If we find signs of life, whether in the form of atmospheric biosignatures or more direct evidence, it could change our understanding of our place in the universe forever. Ultra-red dwarfs, once considered insignificant due to their small size and faintness, may turn out to be the key to unlocking some of the greatest mysteries of existence. In many ways, ultra-red dwarfs are the ultimate paradox. They are both the most common and the least visible stars. They are among the longest-lived yet the least studied. They burn with the weakest flames yet may hold the greatest potential for life. The more we learn about them, the more they challenge our assumptions about the cosmos. They may not shine as brightly as other stars, but in the grand scheme of the universe, their significance cannot be overstated. Ultra-red dwarfs, despite their seemingly unremarkable appearance, could be the foundation of the most abundant planetary systems in the universe. These stars, which are cooler and redder than even the smallest M-type dwarfs, are so faint that they are nearly invisible in optical wavelengths. This makes them difficult to study with traditional telescopes, but their importance cannot be overstated. If planets can form and sustain habitable conditions around these tiny stars, then the number of potentially life-bearing worlds in the universe could be vastly higher than we ever imagined. The fact that ultra-red dwarfs outnumber all other types of stars means that if life does exist elsewhere, it may be more common around these dim stellar objects than around sun-like stars. This raises profound implications for the search for extraterrestrial life and the fundamental nature of habitable environments. One of the most fascinating aspects of ultra-red dwarfs is how they defy conventional expectations about star systems. Traditionally, astronomers assumed that larger, hotter stars would be the best candidates for hosting habitable planets because they emit more light and energy, providing the necessary conditions for life as we know it. However, Our growing understanding of exoplanetary systems has completely shifted this perspective. Ultra-red dwarfs may be small and faint, but they are incredibly stable. Their lifespans stretch far beyond those of larger stars, offering a continuous and steady energy source for trillions of years. This means that any habitable planets orbiting these stars could have an unimaginably long time to develop life, perhaps even longer than Earth has had. However, the unique nature of ultra-red dwarf systems also presents several extreme challenges for planetary habitability. Because these stars are so dim, their habitable zones, the region around a star where liquid water can exist, are much closer than they are around Sun-like stars. This means that planets must orbit extremely near their parent star to receive enough heat to sustain liquid water. But this close proximity leads to a phenomenon called tidal locking, where one side of the planet always faces the star, resulting in perpetual daylight on one hemisphere and eternal night on the other. This creates an environment with stark temperature differences, where the star-facing side may be blistering hot while the dark side remains frozen. The conditions on such planets are unlike anything we experience on Earth, but they may still be capable of supporting life under the right circumstances. Some models suggest that atmospheres on tidally locked planets could circulate heat between the day and night sides, moderating temperatures and making the surface more hospitable. Strong winds and ocean currents could help distribute heat across the planet, creating regions of stable, life-supporting conditions. If an ultra-red dwarf system hosts a planet with a thick atmosphere and a significant amount of liquid water, it could develop a complex climate system capable of supporting life for billions or even trillions of years. Additionally, if life evolved underground or in deep oceans, it could be shielded from the harsh radiation emitted by young ultra-red dwarfs, increasing the likelihood of survival. But one of the biggest obstacles to life around ultra-red dwarfs is their intense magnetic activity. Despite their small size, these stars can produce violent flares, ejecting powerful bursts of radiation that can strip away planetary atmospheres. This is particularly problematic for planets that orbit close to the star, as they are bombarded with high-energy particles that could erode their atmospheres over time. However, some planets may be able to develop strong magnetic fields that protect them from stellar radiation, much like Earth's magnetic field shields us from the sun's solar wind. If a planet can retain its atmosphere despite these challenges, it could remain habitable for an incredibly long time. The idea that ultra-red dwarfs could host life-supporting planets has been strengthened by the discovery of real exoplanets orbiting these stars. The TRAPPIST-1 system is a prime example. This ultra-cool red dwarf, located just 40 light-years away, hosts at least 7 Earth-sized planets, 3 of which are within the habitable zone. The fact that such a tiny, dim star can support a multi-planet system challenges traditional models of planetary formation and suggests that ultra-red dwarfs may be capable of forming far more planets than previously believed. If TRAPPIST-1 is representative of a common type of planetary system, then our galaxy could be filled with similar arrangements, each with its own set of potentially habitable worlds. Another intriguing aspect of ultra-red dwarfs is their potential for hosting rogue planets that do not orbit a star but instead drift through interstellar space. Some scientists speculate that ultra-red dwarfs, due to their low mass and weak gravitational influence, could be the remnants of failed stellar systems that ejected their planets into the cosmic void. If this is the case, then there may be countless rogue planets wandering the galaxy, some of which could still harbor life in subsurface oceans heated by internal geological activity. The possibility of life existing on rogue planets challenges our understanding of habitability, suggesting that biological processes may not be confined to traditional star systems. Another factor that makes ultra-red dwarfs particularly interesting is their potential role in the evolution of intelligent life. Because these stars exist for trillions of years, any civilization that arises in such a system would have an unprecedented amount of time to develop. Unlike Earth, where our sun's lifespan limits the timeframe for life to evolve, a planet orbiting an ultra-red dwarf could theoretically sustain life for a period far longer than the entire history of our universe. This raises fascinating questions about the nature of civilizations that might emerge in these systems. Could they be vastly older and more advanced than anything we can comprehend? Could they have developed technologies that allow them to remain completely undetectable? If extraterrestrial civilizations are common, it is possible that the longest-lived and most advanced among them reside in the stable environments of ultra-red dwarf systems. The vast numbers of ultra-red dwarfs also play a role in the mystery of the Fermi paradox. The question of why, given the high probability of extraterrestrial life, we have not yet detected any signs of it. If life is abundant in the universe and thrives around ultra-red dwarfs, then why have we not encountered any evidence? One possibility is that life in these systems evolves under such stable conditions that civilizations do not feel the need to expand or communicate. Unlike civilizations around hotter, shorter-lived stars, which may be driven by necessity to explore space before their home star dies, civilizations around ultra-red dwarfs could have no immediate survival pressure to leave their planet. They may exist in isolation, focusing on internal development rather than interstellar expansion. Alternatively, the faint nature of ultra-red dwarfs may mean that their planetary systems are simply too difficult to detect with our current technology. If extraterrestrial civilizations are using methods of communication that do not rely on electromagnetic signals, we may be completely unaware of their existence. It is also possible that they have developed energy-efficient technologies that do not produce detectable emissions, making them effectively invisible to us. The idea that the most advanced civilizations could be the hardest to detect aligns with some interpretations of the Fermi paradox, suggesting that intelligent life may be common but hidden from our view. As our technology improves, our ability to study ultra-red dwarfs will continue to expand. The James Webb Space Telescope and other advanced observatories are designed to analyze the atmospheres of exoplanets in infrared light, which is the primary wavelength emitted by ultra-red dwarfs. If we find chemical signatures associated with life, such as oxygen, methane, or water vapor, it could provide the first real evidence that life exists beyond Earth. The discovery of even simple microbial life on a planet orbiting an ultra-red dwarf would revolutionize our understanding of biology and prove that life is not unique to our solar system. The search for extraterrestrial life has long focused on sun-like stars, but the evidence increasingly suggests that ultra-red dwarfs may be the true key to unlocking the secrets of the universe. These dim, ancient stars may not shine brightly, but they could be the quiet hosts of countless habitable worlds, each with its own potential for life. The more we study them, the more they challenge our perceptions of where life can exist. The ultimate question remains, are we alone, or are we just beginning to understand the vast network of life that could be thriving in the shadows of these tiny, red stars? Ultra-red dwarfs, despite being some of the most common stars in the universe, remain one of the biggest mysteries in astrophysics. Their faint glow makes them difficult to detect, and their small size means they are often overlooked in favor of larger, more luminous stars. Yet, these dim celestial bodies could hold the key to some of the most profound questions about the cosmos. If life exists beyond Earth, it may very well be thriving around ultra-red dwarfs, hidden in the perpetual twilight of these long-lived stars. The challenge, however, is proving it. Detecting and studying planets around ultra-red dwarfs is a task that requires cutting-edge technology and innovative techniques. One of the primary obstacles in studying ultra-red dwarfs is their brightness, or rather, their lack of it. These stars emit most of their radiation in the infrared spectrum, making them nearly invisible to optical telescopes. Traditional astronomical surveys often miss them because they are simply too faint to register in visible light. Instead, scientists must rely on infrared observatories, such as the James Webb Space Telescope, JWST, to analyze them. JWST is particularly well suited for this task because it is designed to capture the faint heat signatures of objects that are otherwise undetectable in visible wavelengths. This allows astronomers to study ultra-red dwarfs and their planetary systems in unprecedented detail. The significance of ultra-red dwarfs extends far beyond their potential to host planets. Their unique physical properties make them invaluable for understanding the nature of star formation and stellar evolution. Unlike larger stars, which burn through their nuclear fuel relatively quickly, ultra-red dwarfs are incredibly efficient. They consume their hydrogen at a much slower rate, meaning they can survive for trillions of years, far longer than the current age of the universe. This raises fascinating questions about what happens to a star when it has been burning for an unimaginable length of time. Do ultra-red dwarfs eventually evolve into something else, or do they simply continue burning indefinitely, slowly fading into obscurity? Since no ultra-red dwarf has ever reached the end of its life, we have no direct observational evidence of their final fate. One possibility is that ultra-red dwarfs will eventually become white dwarfs, much like larger stars do when they exhaust their nuclear fuel. However, because these stars burn so slowly, none have had enough time to reach that stage yet. This means that every ultra-red dwarf that has ever formed is still burning today. In contrast, larger stars like our Sun have much shorter lifespans and eventually collapse into dense remnants. If ultra-red dwarfs do evolve into white dwarfs, they could provide crucial insights into the late stages of stellar evolution, insights that are currently impossible to obtain because no ultra-red dwarf has yet reached that phase. Another mystery surrounding ultra-red dwarfs is the nature of their formation. Traditional models of star formation suggest that stars form from the gravitational collapse of massive clouds of gas and dust. However, the process that leads to the creation of ultra-red dwarfs is not fully understood. Some theories propose that they form in the same way as larger stars, but with less available material, resulting in a lower mass object. Others suggest that ultra-red dwarfs might be the remnants of failed star systems, collections of gas and dust that never accumulated enough mass to ignite nuclear fusion in the way that larger stars do. If this is the case, then ultra-red dwarfs could represent an entirely different branch of stellar evolution, one that challenges our current understanding of how stars form and develop. Ultra-red dwarfs also play a crucial role in the study of planetary formation. Because they are so small and cool, their planetary systems are structured differently than those of larger stars. Planets that orbit ultra-red dwarfs must be extremely close to their star to receive enough heat to sustain liquid water. This means that planetary formation around these stars must occur under unique conditions, possibly leading to different types of planets than those found around Sun-like stars. Some models suggest that planets around ultra-red dwarfs may form with thick atmospheres that help regulate temperature extremes, making them more hospitable to life. Others propose that these planets may have large amounts of water, forming global oceans that could support marine ecosystems. One of the most exciting aspects of studying ultra-red dwarfs is the potential for finding exoplanets with biosignatures, chemical signs of life. If a planet orbiting an ultra-red dwarf has an atmosphere rich in oxygen, methane, or other biologically relevant gases, it could indicate the presence of life. The discovery of such a planet would be one of the most groundbreaking scientific achievements in history, proving that life exists beyond Earth. With upcoming missions designed to analyze exoplanet atmospheres in more detail, we may soon have the ability to detect these biosignatures and determine whether ultra-red dwarfs are indeed home to extraterrestrial life. Another major area of research involves understanding the magnetic activity of ultra-red dwarfs. Despite their small size, these stars can produce powerful magnetic fields that generate intense stellar flares. These flares can release massive amounts of radiation, potentially stripping away the atmospheres of nearby planets. However, not all ultra-red dwarfs exhibit this behavior. Some appear to be relatively quiet, emitting only weak flares that may not pose a significant threat to planetary atmospheres. Understanding what causes some ultra-red dwarfs to be more active than others is crucial for determining whether their planets can remain habitable over long periods. Additionally, the longevity of ultra-red dwarfs raises fascinating questions about the nature of alien civilizations. If intelligent life arises around an ultra-red dwarf, it would have an enormous amount of time to develop and evolve. Unlike civilizations around Sun-like stars, which may face existential threats from stellar evolution, civilizations orbiting ultra-red dwarfs could exist for trillions of years. This means that if extraterrestrial life exists in these systems, it could be far older than anything we can imagine. Advanced civilizations might have developed technologies that are completely beyond our comprehension, making them difficult or even impossible to detect with our current methods. Some scientists have speculated that ultra-red dwarf systems could be prime candidates for interstellar colonization. Because these stars exist for such long periods, they could serve as stable homes for advanced civilizations looking to establish long-term settlements. If humanity ever develops the ability to travel between stars, ultra-red dwarfs could become key destinations due to their longevity and potential for hosting habitable planets. The idea of colonizing an ultra-red dwarf system raises intriguing questions about the future of space exploration and the potential for humanity to become an interstellar species. As research into ultra-red dwarfs continues, our understanding of these enigmatic stars will undoubtedly expand. With new telescopes and advanced observational techniques, we will be able to study these faint stars in greater detail, unlocking their secrets and potentially finding evidence of life beyond Earth. The implications of these discoveries could reshape our understanding of the universe and our place within it. If ultra-red dwarfs are indeed home to countless habitable planets, then the universe may be teeming with life, hidden in the dim glow of these ancient, long-lived stars. Ultra-red dwarf stars remain one of the most underexplored frontiers in astronomy, yet their importance in shaping our understanding of the universe cannot be overstated. Unlike their more luminous counterparts, these stars defy easy observation, lurking in the depths of space with barely a whisper of light. Their dim glow means that, for most of human history, they have remained practically invisible, hiding in the cosmic shadows. It is only with the advent of advanced infrared telescopes that we have begun to detect and study these elusive objects. What we have discovered so far is both intriguing and perplexing. These stars are not only incredibly common, making up the majority of stars in the Milky Way, but they also challenge many of our assumptions about stellar physics, planetary formation, and even the possibility of extraterrestrial life. One of the defining characteristics of ultra-red dwarfs is their incredible longevity. While massive stars burn out in mere millions of years and sun-like stars last for billions, ultra-red dwarfs can persist for trillions of years. To put that into perspective, the universe itself is only about 13.8 billion years old. This means that every single ultra-red dwarf that has ever formed is still burning today, with an incomprehensibly long future ahead of it. Theoretically, these stars could still be shining long after the universe has changed beyond recognition, potentially outliving galaxies and even entire stellar civilizations. But what does this longevity mean in practical terms? It means that any planet orbiting an ultra-red dwarf has an almost unimaginable amount of time to evolve life, if conditions allow for it. Astrobiologists have taken a keen interest in these stars for precisely this reason. If life requires stability to develop and evolve into complex organisms, then ultra-red dwarfs offer a stable environment unlike any other. However, stability does not necessarily mean habitability. There are numerous challenges that life around these stars would have to overcome. One of the biggest concerns is stellar activity. Despite their small size, many ultra-red dwarfs exhibit powerful magnetic fields that produce violent flares. These flares can bathe nearby planets in harmful radiation, potentially stripping away atmospheres and making the surface inhospitable to life as we know it. Some researchers have suggested that planets orbiting ultra-red dwarfs might develop thick, protective atmospheres or strong magnetic fields to shield themselves from this radiation. Others argue that life could exist underground or beneath oceans, avoiding the worst effects of stellar flares. Even if radiation isn't an issue, there's another major obstacle: the nature of the light emitted by these stars. Ultra-red dwarfs primarily emit infrared radiation, which is very different from the light our sun produces. This could have profound effects on photosynthesis, the process by which plants and other organisms convert light into energy. On Earth, photosynthesis relies on visible light, particularly the red and blue parts of the spectrum. But on a planet orbiting an ultra-red dwarf, the available light would be dominated by infrared wavelengths. Could life adapt to use infrared light for photosynthesis? Some scientists believe it's possible. Certain types of bacteria on Earth already use infrared light for energy, hinting that alien life around ultra-red dwarfs might function in a similar way. Another challenge is the issue of tidal locking. Because ultra-red dwarfs are so small and dim, planets must orbit them at extremely close distances to remain warm enough for liquid water to exist. This proximity often results in tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. On such a world, one hemisphere would be in constant daylight, while the other would be trapped in eternal night. This could lead to extreme temperature differences, with one side scorching hot and the other freezing cold. However, some models suggest that thick atmospheres or vast oceans could help distribute heat, creating a more temperate, twilight zone along the planet's terminator, the boundary between the light and dark sides. If life were to exist, this narrow strip of habitable land and water might be where it thrives. Despite these challenges, ultra-red dwarfs remain one of the most promising places to search for exoplanets with conditions suitable for life. Their small size makes it easier to detect planets orbiting them using the transit method, which involves looking for tiny dips in the star's brightness as a planet passes in front of it. This technique has already led to the discovery of several intriguing planetary systems around ultra-red dwarfs, including TRAPPIST-1, a system with 7 Earth-sized planets, at least 3 of which are in the habitable zone. While we don't yet know if these planets have atmospheres or liquid water, future telescopes like the James Webb Space Telescope will be able to analyze their atmospheres in detail, searching for signs of habitability, or even life itself. One of the most intriguing possibilities is that ultra-red dwarfs might host planets with biospheres completely different from anything we've ever encountered. Life on Earth is deeply tied to the properties of our Sun, but life around an ultra-red dwarf would have evolved under vastly different conditions. The lower energy output of these stars, combined with their infrared-dominated spectrum, means that any organisms living there would need unique adaptations. Perhaps plants would be black instead of green, absorbing as much infrared light as possible. Perhaps animals would rely on heat-sensitive vision rather than eyesight based on visible light. The chemistry of life itself might be different, with biological processes operating at lower energy levels than those on Earth. There is also the question of what happens to ultra-red dwarfs over truly immense timescales. Since no ultra-red dwarf has yet reached the end of its life, we can only speculate about their eventual fate. Unlike larger stars, which end their lives in violent supernovae or by collapsing into white dwarfs, ultra-red dwarfs are expected to simply fade away. They will gradually burn through their hydrogen, becoming dimmer and cooler over trillions of years. Eventually, they will transition into what some astronomers call a black dwarf, a theoretical object that is so cold and faint that it becomes virtually undetectable. However, since the universe is still young compared to the lifespans of these stars, no black dwarfs yet exist. This means that ultra-red dwarfs represent a kind of cosmic time capsule, allowing us to glimpse the distant future of stellar evolution. Their long lifespans also raise fascinating questions about the possibility of ancient extraterrestrial civilizations. If intelligent life arises around an ultra-red dwarf, it could have billions or even trillions of years to evolve, far longer than life on Earth has had. Such a civilization might develop technology that is completely beyond our understanding, possibly even achieving a level of advancement that allows it to manipulate entire planetary systems or harness the energy of its star in ways we can't yet imagine. If such civilizations exist, could they have left behind evidence of their presence? Could we detect artificial structures or unusual energy signatures around ultra-red dwarfs? So far, our searches have come up empty, but that doesn't mean they aren't out there. Ultra-red dwarfs may be small and faint, but their importance in shaping our understanding of the universe is enormous. They challenge our ideas about star formation, planetary habitability, and even the nature of life itself. As we continue to explore these enigmatic stars, we may uncover answers to some of the biggest questions in science. Could life exist in the dim glow of an ultra-red dwarf? Could these stars outlive everything else in the universe? And could they be home to civilizations that have watched the cosmos evolve for eons? The search for answers is just beginning, and as our technology improves, the secrets of these ancient, overlooked stars may finally be revealed. Ultra-red dwarf stars stand as the quiet sentinels of the universe, their dim glow illuminating the depths of space for longer than any other type of star. Unlike the massive, short-lived giants that explode in spectacular supernovae, these tiny stars burn through their fuel so slowly that their lifespans stretch into trillions of years. So long, in fact, that not a single one has ever lived long enough to die. This makes them unique time capsules of stellar evolution, existing across cosmic epochs in ways we can barely comprehend. They were among the first stars to form after the birth of the Milky Way, and they will likely be the last stars still burning when the universe itself reaches its twilight. But while their longevity is fascinating, the mysteries surrounding them run even deeper, raising fundamental questions about planetary formation, the nature of alien biospheres, and even the ultimate fate of the cosmos. One of the most puzzling aspects of ultra-red dwarfs is their surprisingly high frequency. When astronomers began surveying the skies with advanced infrared telescopes, they expected to find these stars in significant numbers, but what they discovered was astonishing. Ultra-red dwarfs account for the vast majority of stars in the universe, yet they are so faint that they remained hidden from view for most of human history. Even in our own cosmic backyard, many of the closest stars to the Sun were only identified recently, lurking in the darkness just beyond the reach of visible light telescopes. The sheer abundance of these stars suggests that the traditional image of the night sky, filled with bright, twinkling points of light, is misleading. If human eyes were sensitive to infrared radiation, the night sky would look vastly different, with a dense web of dim, cool stars filling the void between the brighter, more massive stars we can currently see. Their prevalence also means that they likely host a staggering number of planets, many of which could be Earth-sized. The discovery of exoplanets around ultra-red dwarfs has been one of the most exciting breakthroughs in modern astronomy, challenging our understanding of planetary formation. Traditionally, scientists believed that small, cool stars would struggle to form planets, especially large rocky worlds like Earth. However, observations from telescopes like Kepler and TESS have revealed that ultra-red dwarfs often have tightly packed planetary systems, with multiple Earth-sized worlds orbiting in close proximity. Some of these planets reside in the so-called habitable zone, where temperatures could allow liquid water to exist, a crucial ingredient for life as we know it. But the conditions on these planets are unlike anything found in our solar system, raising questions about whether life could truly survive there. The challenge of habitability around ultra-red dwarfs is one of the most hotly debated topics in astrobiology. On one hand, the extreme longevity of these stars provides an unparalleled opportunity for life to emerge and evolve. If complex life takes billions of years to develop, then a star that remains stable for trillions of years might offer the perfect environment. On the other hand, these stars exhibit behaviors that could make life extremely difficult, if not impossible. One of the biggest problems is stellar activity. While ultra-red dwarfs are small and dim, they often produce powerful magnetic fields that generate violent stellar flares. These flares can release bursts of X-rays and ultraviolet radiation, bombarding any nearby planets with intense energy. If a planet lacks a strong magnetic field or a thick atmosphere, it could lose its atmosphere entirely, leaving the surface exposed to deadly radiation. Some researchers argue that life might still find a way to persist. On Earth, certain microorganisms thrive in extreme environments, from deep-sea hydrothermal vents to the frozen tundras of Antarctica. If life can survive in such harsh conditions here, it might also endure the extreme environments of ultra-red dwarf planets. One possibility is that life could exist beneath the surface, shielded from radiation by thick layers of rock or ice. Alternatively, life might develop mechanisms to repair radiation damage, similar to how some extremophiles on Earth have evolved to survive in high-radiation environments. Another intriguing idea is that planetary atmospheres could regenerate over time. Even if a flare strips away part of an atmosphere, volcanic activity or geological processes might replenish it, allowing life to persist in cycles of destruction and renewal. But radiation is not the only obstacle. The way these planets are locked in gravitational embrace with their stars creates another challenge. Because ultra-red dwarfs are so cool, planets must orbit extremely close to receive enough warmth, often completing an orbit in just a few days. This close proximity results in tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. The day side might be scorching hot, while the night side could be frozen solid, creating an extreme and hostile environment. However, some models suggest that an atmosphere, if present, could help distribute heat more evenly, creating a habitable twilight zone along the boundary between the two hemispheres. If such a world harbors life, it could exist in this narrow, dimly lit strip of land and ocean, a permanent dawn or dusk where conditions are just right for survival. Even more fascinating is the possibility that life on these planets would be fundamentally different from anything found on Earth. Since ultra-red dwarfs emit mostly infrared light, any photosynthetic organisms would have to adapt to this energy source. Instead of green plants, which rely on visible light, alien vegetation might be black or dark purple, optimized to absorb as much infrared radiation as possible. The biochemical processes of life might also differ significantly, with organisms evolving to operate at lower energy levels. Could such life forms develop intelligence? Could entire alien civilizations exist in the dim glow of an ultra-red dwarf, building societies and technologies unlike anything we've ever imagined? The search for planets around ultra-red dwarfs is still in its early stages, but upcoming telescopes promise to revolutionize our understanding of these mysterious stars. The James Webb Space Telescope, JWST, is already beginning to analyze the atmospheres of exoplanets, looking for signs of habitability and even biosignatures, chemical indicators that could suggest the presence of life. Future missions, like the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, will provide even more detailed data, allowing us to peer into the atmospheres of planets orbiting these stars with unprecedented precision. If life exists in these distant systems, we may soon have the tools to detect it. Beyond the search for life, ultra-red dwarfs may also hold clues about the far future of the universe. Since these stars burn their fuel at an incredibly slow rate, they will outlast all other types of stars. As larger stars die off, fading into white dwarfs, neutron stars, and black holes, ultra-red dwarfs will continue to burn. They will be the last sources of light in a darkening cosmos, shining on even as galaxies fade into the abyss. Eventually, after trillions of years, they too will exhaust their fuel, transitioning into a state known as a black dwarf, a theoretical object so cold and dark that it emits no detectable radiation. No black dwarfs exist yet, as the universe is still too young, but they represent the final stage of stellar evolution for ultra-red dwarfs. This raises profound questions about the ultimate fate of life in the universe. If civilizations arise around ultra-red dwarfs, they may have trillions of years to evolve and advance. What kind of technology could emerge over such immense timescales? Could these civilizations find ways to escape the eventual cooling of their stars, migrating to new energy sources or even manipulating fundamental laws of physics? And if such civilizations exist, could we detect them today, hidden among the countless ultra-red dwarfs that populate our galaxy? Ultra-red dwarfs may be the smallest and faintest stars in the universe, but they hold some of the greatest cosmic mysteries. Their sheer abundance makes them critical players in the story of the cosmos, from the formation of planets to the evolution of life and the distant future of the universe. They challenge our perceptions of habitability, forcing us to reconsider what it means for a world to be livable. They push the boundaries of stellar physics, showing us how stars can defy the usual expectations of size and longevity. And perhaps most importantly, they may be the key to answering one of the greatest questions of all: are we alone in the universe? Ultra-red dwarf stars may seem unremarkable at first glance, but their presence in the universe raises profound questions about the nature of stellar evolution, planetary formation, and even the limits of life itself. They are the dimmest, coolest, and longest-lived stars, quietly burning through their fuel at a rate so slow that none have yet reached the end of their lifespans. This means that studying them is like peering into a cosmic time capsule, one that holds secrets stretching from the distant past to the distant future. Their extreme longevity makes them unique in the grand scheme of cosmic evolution, as they will remain long after all other stars have faded away. But despite their vast numbers, these stars remain elusive, hidden in the shadows of brighter celestial objects. It is only through recent advancements in infrared astronomy that we are beginning to uncover their mysteries. One of the most intriguing aspects of ultra-red dwarfs is their connection to planetary systems. In the past, astronomers assumed that small stars would struggle to form planets, particularly large rocky worlds like Earth. However, observations from telescopes such as Kepler and TESS have overturned this assumption, revealing that ultra-red dwarfs frequently host planetary systems. Not only do they have planets, but many of these planets are Earth-sized, and some even exist within the so-called habitable zone, where temperatures might allow for liquid water to exist. This discovery has profound implications for the search for life beyond Earth. If planets around ultra-red dwarfs are common, then habitable worlds could be far more numerous than previously thought. However, the conditions on these planets are vastly different from those in our solar system. Because ultra-red dwarfs are so cool, their habitable zones are incredibly close to the star itself. This proximity means that planets often experience tidal locking, where one side is permanently bathed in the dim glow of the star, while the other remains in perpetual darkness. This extreme environment poses significant challenges for life as we know it. The day side of the planet might be scorching hot, while the night side could be frozen solid. However, some scientists believe that if these planets have thick atmospheres, they could distribute heat more evenly, creating a habitable twilight zone along the boundary between the hot and cold hemispheres. Another major challenge is the intense stellar activity of ultra-red dwarfs. Despite their small size and low energy output, these stars are known for their powerful stellar flares. They produce sudden bursts of radiation, including high-energy ultraviolet and X-rays, which could be devastating to any nearby planets. If a planet lacks a strong magnetic field, these flares could strip away its atmosphere over time, exposing the surface to lethal radiation. This has led some scientists to question whether planets around ultra-red dwarfs can truly support life. However, other researchers argue that life might adapt to these extreme conditions. Some organisms on Earth, such as those found in radioactive environments, have developed mechanisms to survive intense radiation. If life exists on these planets, it might be deeply buried beneath the surface, protected from the harsh stellar environment. The nature of photosynthesis on these planets is another fascinating topic. Since ultra-red dwarfs emit mostly infrared radiation, traditional green plants, which rely on visible light, might not survive. Instead, alien vegetation might be black or dark purple, optimized to absorb as much infrared light as possible. The biochemistry of life in these systems could be radically different from anything found on Earth, operating at lower energy levels and adapting to a world of eternal twilight. If intelligent life were to evolve under such conditions, their entire perception of the universe might be shaped by an existence in the dim glow of a faint star. The search for life around ultra-red dwarfs is just beginning, but upcoming telescopes promise to revolutionize our understanding. The James Webb Space Telescope, JWST, is already analyzing exoplanet atmospheres, searching for signs of habitability and even potential biosignatures. Future telescopes, such as the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory, will provide even more detailed observations, allowing scientists to study these distant worlds with unprecedented clarity. If life exists in these systems, we may soon have the ability to detect it. Beyond the search for life, ultra-red dwarfs may hold clues about the ultimate fate of the universe. Because they burn through their fuel at an incredibly slow rate, they will outlast all other stars. As larger stars die, fading into white dwarfs, neutron stars, and black holes, ultra-red dwarfs will continue to shine. They will be the last sources of light in a universe that is slowly growing colder and darker. Eventually, after trillions of years, even they will exhaust their fuel, becoming black dwarfs, hypothetical objects so cold and dark that they emit no detectable radiation. No black dwarfs exist yet, as the universe is still too young, but they represent the final stage of stellar evolution for these long-lived stars. This raises profound questions about the fate of life in the universe. If civilizations arise around ultra-red dwarfs, they may have trillions of years to evolve. What kind of technology could emerge over such immense timescales? Could these civilizations find ways to escape the eventual cooling of their stars, migrating to new energy sources or even manipulating the fundamental laws of physics? If such civilizations exist, could we detect them today, hidden among the countless ultra-red dwarfs that populate our galaxy? Ultra-red dwarfs may be the smallest and dimmest stars, but they hold some of the greatest mysteries in the cosmos. They challenge our understanding of planetary formation, push the boundaries of habitability, and force us to reconsider what it means for a world to be livable. As our technology advances, we will continue to uncover the secrets of these enigmatic stars, and perhaps, one day, we will find that they are home to life unlike anything we have ever imagined. Ultra-red dwarf stars are not just mysterious because of their small size and faint glow. They challenge nearly every assumption astronomers once held about the formation and longevity of stars. Unlike the massive, short-lived giants that burn through their fuel in mere millions of years, ultra-red dwarfs operate on a completely different timescale. Their lifespans stretch into the trillions of years, meaning that in the entire history of the universe, not a single one has yet reached the end of its life cycle. This simple fact makes them a kind of cosmic anomaly, objects that exist on a scale of time so vast that human civilization, and even the Earth itself, will be long gone before these stars even begin to die. The reason ultra-red dwarfs last so long comes down to their incredibly efficient use of hydrogen fuel. Unlike larger stars, which burn hydrogen rapidly in their cores, ultra-red dwarfs mix their fuel throughout their entire volume, preventing the buildup of inert helium that eventually chokes larger stars. This process, called full convection, ensures that no hydrogen goes to waste. Instead of forming a dense helium core like the Sun does, ultra-red dwarfs keep their fuel circulating, allowing them to sustain nuclear fusion at an extremely slow rate. This is why they shine so dimly. They are essentially stretching their energy reserves across a timeline far beyond human comprehension. Because of their immense lifespans, ultra-red dwarfs are expected to outlast all other stars. When our Sun reaches the end of its life in about 5 billion years, swelling into a red giant before collapsing into a white dwarf, ultra-red dwarfs will still be burning as if nothing has changed. In fact, even after another 10 trillion years, when every other type of star has either died or become a cold, lifeless remnant, ultra-red dwarfs will still be glowing faintly in the darkness. It is only after tens of trillions of years, far beyond the current age of the universe, that these stars will finally exhaust their fuel, fading into hypothetical black dwarfs. But before they reach that final stage, ultra-red dwarfs will have an enormous impact on the planets that orbit them. The question of habitability remains one of the biggest mysteries surrounding these tiny stars. On one hand, their longevity provides a stable environment for planets over unimaginable timescales. Any life that forms in these systems could have a vastly longer window to evolve than life on Earth. However, the conditions around these stars are anything but ideal. Their habitable zones are so close to the star that planets often become tidally locked, meaning one side always faces the star while the other remains in permanent darkness. This results in extreme climates, with one hemisphere experiencing constant scorching daylight, while the other endures eternal freezing night. The atmosphere of a planet around an ultra-red dwarf could determine whether life has any chance of surviving these harsh conditions. If the atmosphere is thick enough, it might circulate heat, creating a more temperate, twilight zone, between the scorching day side and the frozen night side. However, there is another major challenge: stellar activity. Ultra-red dwarfs are known for their violent and unpredictable stellar flares. These flares can be dozens, even hundreds of times more powerful than those from the Sun, bombarding nearby planets with deadly radiation and stripping away their atmospheres. Despite this, some scientists argue that life might still find a way. If a planet has a strong magnetic field, it could shield its atmosphere from the worst effects of stellar flares. Additionally, life could evolve to survive underground or beneath oceans, where it would be protected from radiation. Certain Earth organisms, such as extremophiles, have already demonstrated the ability to thrive in environments with extreme radiation exposure. If similar forms of life exist elsewhere, planets around ultra-red dwarfs might not be as barren as they seem. The question of whether planets around ultra-red dwarfs can support photosynthesis is another major unknown. Since these stars emit mostly infrared light rather than visible light, traditional photosynthesis, as we know it on Earth, might not work. Instead, alien plants, or their equivalent, would need to evolve a way to absorb infrared radiation. This could lead to entirely new forms of biological energy production, unlike anything found on Earth. Some scientists speculate that vegetation on these worlds could be black or dark colored, optimized to absorb as much of the dim starlight as possible. If life does exist around ultra-red dwarfs, it could be vastly different from anything we can imagine. And if intelligent life emerges, its perception of the universe would be shaped by the faint, reddish glow of its home star. Civilizations that evolve under such conditions might never see true daylight as we do on Earth. Instead, their entire history would unfold under the eerie twilight of an ultra-red dwarf, influencing everything from their biology to even their understanding of the cosmos. As our technology advances, we are getting closer to answering some of these questions. The James Webb Space Telescope is already providing new insights into exoplanet atmospheres, and future telescopes will allow us to study these distant worlds in even greater detail. If we find signs of life around ultra-red dwarfs, it will completely change our understanding of habitability in the universe. But beyond their role in planetary systems, ultra-red dwarfs also hold clues about the far future of the universe. Since they will outlive all other stars, they will be the last sources of light before the cosmos fades into darkness. As the universe continues to expand and galaxies drift apart, ultra-red dwarfs will remain, slowly burning through their fuel while the rest of the cosmos grows cold and empty. This leads to one of the most profound questions of all. If advanced civilizations arise around ultra-red dwarfs, could they find a way to escape the inevitable death of the universe? Would they seek out new energy sources, harnessing the power of black holes or even manipulating the fundamental laws of physics? Could they leave the universe entirely, venturing into other dimensions or parallel realities? Ultra-red dwarfs may be small and faint, but they are some of the most fascinating objects in the cosmos. They challenge everything we thought we knew about stars, habitability, and even the fate of the universe itself. As we continue to explore their secrets, we may find that they hold the key to understanding not just the past and present of the cosmos, but its ultimate destiny. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.